Thank you. So, hello everyone. I'm Pedro from the University of Porto. And I'm going to talk to you about an interpreter, a lightweight interpreter that we developed for teaching functional programming. So this is joint work with Rodrigo Marques, who's also there. And so let's start with a bit of context. So we teach functional programming as a first-year course. It's not the first programming course they have, but it's a first-year course. And it's a standard curriculum, so evaluation by rewriting, recursion, data types, higher-order functions, etc. And I found about a year and a half ago that I really wanted a lightweight tool that could be used to show that the computational model of functional programming, so show equational reasoning where each step in your computation is justified by one of your program equations. In this style, the style of the textbooks by Bird, Wadler, etc. I wanted this to be web-based, so I didn't want students to have to install anything. And the point wasn't really to replace completely GHC or GHCI. We still use it because I want them to make larger programs. I want them to see functional programming as something that they can build their exercises in and build future projects in. So here's an example of the sort of thing I want to build. So if the student writes that program and asks to evaluate that expression. So the program is an insertion into a list that's supposed to be ordered and maintaining the ordering. It will produce a step-by-step trace like this with the equations in between. So rather than do this, I'll just show you how it works. So I have this prepared, but this is an editor. The students can change anything, evaluate, and then go step by step until they reach the final result. Okay? You can also hide the justifications, and they will appear as sort of tooltips over there. So this is what I want to get. So how did we come to this? So this required a slightly new look at the way you do this evaluation. So a new core language based on a pattern matching calculus. The idea is to have explicit treatment of the nested patterns and failure. And the reason for this is that I want a close relation between what I am executing and what the student wrote. I don't want to have a huge semantic gap, a translation between the two. Then I developed a big step semantics based on the one of Lunchbury, a small step semantics for the abstract machine, which is actually the thing that we do implement, because the big step semantics requires you to do the whole evaluation at once, and I want to do it piecewise. There's a correspondence between the two semantics, a sketch of the proof. It's not particularly difficult, but it's in the paper. And some extensions that I'm going to show you for bank patterns, for example, that allows us to show lazy evaluation at work. The implementation is freely available. You don't need to install anything. You can just test it on web. So but let's first start with this idea of why do I need a pattern matching calculus? So the standard technique in lazy functional languages for implementing pattern matching, nested patterns, overlapping patterns, is to translate them into simple cases like those. That's a function that's supposed to tell me if a list is short. So if it has at least 2 elements, it's not short, otherwise it is short. But the translation that something like GHC will do is do the thing on the right. There's a single equation, a case that takes apart a constructor and at one level only. So there's one constructor and variables, and then again, one constructor and variables, and you have to cover all the cases there. So why is this done? So the big advantage is that in a lazy language, you don't want to over-evaluate. So this way, you evaluate just as much as you need to make the next decision. So a simple case forces evaluation just to the outermost constructor. You don't need backtracking. You don't need any way of handling the failure except as a sort of panic or something like that. And in practice, it can be implemented very efficiently because it's almost like a machine-level switch. There's variable binding as well, but that's not particularly difficult. The disadvantage is that doing this translation isn't straightforward. I call it non-local in the sense that you have to have a global view of the equations in your program, and you have to be careful to avoid duplicating work. So there's a whole chapter of the classic implementation of functional language book dedicated to that. And the thing is that when you reach the final program, then the thing you're going to execute no longer relates to the original program. It's not easy to point out which equation was used at which point, and this gets even more complicated. You have things like guards or So what's the alternative? The alternative we employ is a pattern matching calculus. And this is how it's going to look in our pattern matching calculus that I'll show you in formal detail later. If you squint, it sort of looks like lambda case, but it's a little bit more general than lambda case for composition of the evaluation. So the idea is that you have nested patterns, you have a notion of alternative and a notion of failure, explicit failure in the calculus, and so the operational semantics actually does something closer to what the programmer wrote. And it's less efficient because you have to manage this alternative backtracking, but that's not a major concern in a tool where you're going to use it for small programs anyway. Okay, so this is what I'm going to go through. First, the syntax. So I call this Lambda PMC. The original work is called PMC. It's by Wolfram Kahl. And it's essentially the same thing except for some syntactic notation differences and adding a form of local bindings. So there are three syntactical categories. So we have expressions, as in the lambda calculus, as in core, but we also have matchings and patterns. So expressions are on the left, matchings on the right, patterns on the bottom. Expressions and patterns are mutually recursive. So expressions can contain matchings, and matchings can contain expressions. The patterns only occur inside matchings. They don't occur in expressions. So let's look at these in more detail. So the first few cases are just like the lambda calculus. There are variables, free variables. There's application. But then you don't have a lambda abstraction. You have lambda, which simply injects a matching as an expression. So it's taking a matching and treating it as an expression. A matching will represent functions, but not just functions. You could have sort of already fully applied functions as well. And you have constructors. And constructors, as in core and STG, are supposed to be saturated. So you don't under-apply a constructor. Then you have matchings, and matchings have a few cases. So the first case is the case where you already know the matching succeeded, and you're going to continue with some expression. That's the success. The second case is a failure, when you haven't matched your input. And the third is a function expecting a result that matches some pattern and continues with some matching. The third is a supply of an argument, so it's really just another form of application. So this is like application, but it's written in reverse order. So the argument is here in the E, and the matching is the continuation. So this is what allows us to be compositional. I'm not actually going to show you the matching rules here, they're in the paper, but we want to make this compositional. So define the semantics of matching by splitting apart the constructors and continuing matching smaller things. And this construct is what allows this. By the way, this syntax is from Cal. And then we have alternatives, and we have a way of doing local bindings. Patterns are just variables or constructors with more patterns, so you can have nested patterns. So let's look at how this works for translating something like Haskell. So I'm not going to do a formal translation because I would need a formal definition of Haskell, and that's beyond the scope of this work. So the general idea is that the translation is quite straightforward to do. Multiple equations will correspond to a binding with a matching with multiple alternatives. If you have overlapping or nested patterns, you don't change them, you just leave them as they are. Case expressions, ifs, guards are all special cases of matchings. So here are some examples. Just as expression, a lambda, that really translates to lambda and then a matching with the same variables. So that's why I'm using this symbol for injecting a matching, because most of the cases this will be a function. But this is not a function. This is an expression with some free variables that supposedly are in context. It's still translated to an expression that looks like a matching. So it's lambda, and then here you have the argument that's been supplied to the alternatives. True will be this case, false will be that case, and you have to go back to expressions at the end. So this is a definition of binding. So this will be translated into a binding, but the right-hand side is always a single expression, including matching. In this case, there's no definition for the empty list, so it only includes this case. This one has two equations that they translate to two different branches in the matching. And this is the first example we saw. So here is a more complex example using guards. and has patterns as well. So here I have an equation that applies when the list has at least 2 elements. I named the sub-expression, the sublist there, and I also have a guard saying that they have to satisfy this predicate. So I have to do computation while doing matching. So this has to be something that has to be executed while doing the matching. And it turns out you can do these things by this interleaving between matchings and expressions. So there's a first argument, which is this outer pattern. Then you take the second argument and you match it against the sub-pattern. And then you match the guard against true. And if all of these things succeed, then you go on to the recursive call. The second case is the translation of this equation. It doesn't need to consider whether this happened or not, because the ordering here matters. The first case will be tried first, and the second. And the final case is the empty list. It's also possible to encode more sophisticated things like pattern guards and view patterns. That was already noted by Cal in the original paper. By the way, this translation is also in the original paper. It's nothing new here. So what is new? One of the things is having the naming mechanism for sharing, something like a let binding. But I called it where instead of let. And why is that? Because we do need both, because we have 2 syntactic categories. We have expressions and matchings. And this is analogous to what happens in Haskell. You can use let for expressions and where for bindings. And where, for example, you can find names that scope over a guard, whereas with let, they will only scope over the right-hand side. So by analogy, what I used was where when I define the bindings in matchings. And it turns out that you don't actually need the let, because you can define the let by a simple translation into a where. So let will be a lambda with no argument that just has the expression where the bindings. So this way, I can just have one of them. Well, you could ask, why did I choose the where and not the let? Well, the let isn't so easy to use as a primitive for defining the where, because matchings can fail and expressions don't fail. When you get an expression, you can't go back and say, oh, that was not the case I wanted to treat. So I take where as a primitive and let is syntactic sugar. So now we're going to the semantics. So the idea is defining the simplest form of semantics that I can do to give an interpreter. And that's an operational semantics, a natural operational semantics, based on launch-with semantics. Actually, Sestov's revision of launch-with semantics. The first thing we have to realize is that it's very important not to duplicate work. So we have to work on normalized terms. This means arguments to applications, so the arguments to applications in expressions and applications in matchings. Both of them need to be simple variables. I'm using y to mean that they are not bound. They're sort of free somewhere and not bound. The arguments of constructors themselves must be simple variables. And then we have a heap that captures these free variables around. A heap is simply a mapping from free variables to expressions. The expressions can be suspended, like funcs, or they can be reduced, already reduced. And these are used to memorize evaluations. And there are 2 mutually recursive judgments: evaluate expressions, evaluate matchings. So let's look at what this shape of the judgment looks. This is just like launch with semantics for expressions. So this is initial heap. This is a technical add-on, which is a list of things that are, a set of variables that are under evaluation. It's only required to define the notion of freshness. And then we have the expression, the final heap, and the result. And what is the result? It's a generalization of the notion of weak head normal form, typical of functional languages, lazy functional languages. So it's either a constructor with evaluated to the outermost form. So you know the outer constructor, but the inside are variables that can point to unevaluated things, or it's a lambda, but not any lambda. It has to be expecting at least one argument. If it is already saturated, then it's still not our normal form. We have to reduce it further. And this symbol means arity. It's defined in the paper. It's a simple syntactic measure over the term. And we have a matching an evaluation for matchings as well. And this is new because now the result isn't a weak head normal form. So we also need the heap. And we need the set of variables for the freshness condition. We need another argument, another stack, which is a stack of things that are being supplied to the matching. This is for compositionality when you go inside the patterns. You need the matching you're going to execute, and the final heap. So matching will possibly change the heap, because matching will provoke evaluation. So you can have further things being evaluated, and you have to record, memorize those results. So you have to get the heap in and the heap out. And what is the result? It's either a success expression, so this matching, or a failure. And both are defined in the paper. I'm not going to go over them here. So this is my specification, and this is designed to ensure that I believe this is doing a lazy evaluation. But to implement a step-by-step interpreter, I need something where I can stop the evaluation partway through. And that's really just turning that big step semantics into a small step semantics. And it looks like this. There's a state configuration, and each reduction is a change in the configuration. So there's a heap, there's a control, which is essentially which of the modes you're doing the evaluation, because you're going to be alternating between expressions and matchings. And there's a return stack, which is essentially the continuation. I call it a list of continuations, but technically the whole thing is the continuation. And the paper has the transition rules. Okay, so this is the formal basis for the implementation. So, but there are still things to do. How is the implementation done? It's written in Elm, and it compiles to JavaScript, so the whole thing runs on your web browser. There's no server. You don't need to connect to anyone. You can copy the assets or clone it into your machine and have it running locally on your internal network. It implements a reasonable subset. So it implements more things than the model, the semantics, so things like integers, characters. You can define your own data types and define the constructors. Multiple equations, nested patterns, guards, cases, let where. A lot of the prelude functions are there, they're predefined. You can define them yourself, redefine them if you want to use a different version to show the different operational aspects. It does parsing using an Elm parser combinator library, does type checking and step-by-step evaluation. And there are some extensions that I'm going to show for bank patterns and forcing evaluation. By the way, this GitHub page has the actual demos. There's lots of demos you can try there. You can run it on a smartphone. It's fast enough to run on a smartphone, no problem there. So how does the parsing and type checking work? Pretty standard stuff. There's nothing very sophisticated here. I build an enriched AST just so that I allow better error messages, or I should actually say less bad error messages. We'll come to that. Type checking and inference is very simple. It's just Hindley-Milner. There are no type classes. There's monomorphic arithmetic. It's only one num type, which is int. There is a polymorphic equality, but it's implemented ad hoc as structural equality inside the interpreter that may fail if you supply, say, a function to it. No higher kinded types, just simplify kind inference. And the step-by-step evaluation, how is it done? So, we implement the abstract machine transitions almost exactly as they are in the paper, but there are some primitives for integers and characters. Those are not particularly difficult. How do we do normalization? We build special variables that we call indirections that can be detected and short-circuited during presentation. So this is what allows presenting the evaluation as if it was on expressions, even though it is graph reduction. So I don't want to show to the students the heap and pointers going around. I want to keep the illusion that you're doing term rewriting on strings or expressions, but actually have the lazy evaluation, because I want to do non-strict evaluation, and this is more efficient if I do it this way. There's still a problem, which is, if you look at the paper, I haven't shown you here, there are lots of rules, lots of configurations, and it's very technical, and I don't want to overload students with that. I mean, these are not PLT students. These are first-year students. I can't show them the Lambda PMC. They are starting with Haskell, so I can only show them things that look like Haskell. So what do? I want to avoid showing all transitions, just show some of them. And I come up with an heuristic that actually works really well, and it's very simple. You only show a configuration in two cases. After you've done a primitive, like after you've evaluated plus with two concrete integers, you get 3, that's shown. And after you've done a successful matching. So whenever you reach something that is like that matching with a return expression, you will show that to the students. And you pretty print it in a way that it looks like an expression. I never show things that are specific to the Lambda PMC. So how do I show? I mean, showing the primitives is easy because I can just pretty print them in the interpreter. But how do I show the equations? And the solution here is very low tech, but it works well, which is when you do the parsing, just annotate each of these return expressions with the program text that led to that part. So this is what it would look like for the initial example that I've shown you. So this is the original program, and this is actually what we do build inside our interpreter. And note that every of those return expressions has a string, and the string is taken from what the student wrote or what the programmer wrote. And the advantage here is that you get you don't have problems of having done some sort of desugaring or some sort of simplification that you then have to revert back when you're showing to the user. You just use whatever they chose as a way of writing the program. Yeah. So what else can this do? It's very easy to add some evaluation extensions. So bank patterns is one of them. That actually wasn't in Cal's original calculus. I mean, Cal's calculus was just a calculus. It just proved confluence. It didn't care about a reduction strategy. So the concept of strictness and doesn't really make sense in that setting. But it does in Haskell. And so we can use bank patterns and define fold L prime as well as fold L. And the difference, if you notice, is just this little annotation here. Whenever you take the accumulator in the recursive case, force it before continuing. And this allows us to show what a space leak is simply by term rewriting, simply by looking at expressions. The evaluation rules are simple and they're in the paper, but I'm going to show you what it looks like. So the left side is the lazy fold L. The right side is the strict fold L prime. And the operator we're using is times with a list of integers. And if you look at the lazy version, you can see that it's building up in the accumulator position this expression that mimics the original list. And at the end, you then get to reduce it all down to a number. So it's building up the expression and then reducing. And if you force the evaluation at this point, then what you get is that each step of the reduction, you force the evaluation of the accumulator and then continue with the accumulator forced. So you end up interleaving the work of computing the accumulator with the recursion, which is exactly what you want to avoid this space leak. So notice that the number of steps is exactly the same. So it's doing the same work, but it's distributing it differently. And I don't have to talk about thunks or look at core or look at STG. It just comes out of the rewriting. So there are more examples in the paper. For example, if you have a pair, you can show what happens if you have outer strictness but not strictness inside the pair. You still get the space leak. So it's all composes very well. Okay, so some related work. There's lots of work for teaching Haskell and teaching reductions. And so here are some interesting prior work. So HAT is a tracing tool for Haskell programs. It works by instrumenting your program, so you have to import the library, annotate it, compile, run it, and then use an external program to look at the traces and do something. It doesn't actually annotate the steps, it just shows how you call the function, so what arguments you use to call each function. And this whole annotate your program, compile, run, it's a much higher entry barrier. It's hard enough getting students to install GHC and then asking them to install an extra library and doing some annotation. It's a lot of syntactic overload, and I wanted to avoid all that. More recently, there's this Haskell expression evaluator, which is based on term rewriting. This is really based on term rewriting. It supports different strategies, so You could do outermost or innermost. I think not lazy evaluation, so we could do a call by name or outermost reduction, but not lazy evaluation. It can show the evaluations and check students' evaluations, but it is a tool that requires lecturers to provide some exercise, and then students can fill the exercise, but they can't put in their own definitions. And there's more related work in the paper. So, conclusion. So we have a lightweight step-by-step interpreter for a small subset of Haskell. It's not a new problem. I mean, most of the citations in this paper are quite old because of that. But what I want to point out is that there are different trade-offs that led to a different decision. In particular, I care more about how do I present the results to my students, how do I lower the barrier for experimenting with this evaluator. One thing that I learned when doing this is that lazy evaluation and pattern matching really are interact in subtle ways. Pattern matching is more subtle in lazy languages than it is in strict languages. For example, we really need interleaving between evaluating and matching. You can't split the two apart. And the other thing is the formal semantics really helped this implementation, because what I'm showing you is not the first version of this work. The first version was a bit of a hack, and I gave up on time and said, no, I teach this stuff. I should be able to do this on a more fundamental basis. So for further work, we're doing an educational assessment. So the last semester we taught functional programming using Haskellite. We asked students for feedback. Spoiler alert, a better error message is what every student asked for. Things we're not doing, bindings with patterns. You can't do let P, where P is a pattern, equals an expression. This is a bit subtle because the semantics there is that you should be lazy in the patterns. It's what the Haskell's report calls the irrefutable patterns. So list comprehensions, we don't do that as well. The reason for not doing it is that we'd have to translate them to things like concat map with filter, but list comprehensions are usually introduced before higher order functions. So this would lead to a situation where the code that the students run doesn't look like what it wrote. Type classes, well, I'm not sure they should be put there. You could put them, but then you get the problem of dictionaries coming up around, and again, some artifact that the student didn't write appearing in the execution. IO and effects, same thing. So, and with this, I'm ready to take some questions.
The impression I get from the talk is that in this class that you're teaching, the meaning of a program can only be arrived at evaluating it in a very special way.
Yeah.
Do you teach in your class then? Or perhaps I can ask, how do you teach in your class then? Yeah. The concept of non-strict semantics.
Yeah. You're right. What you're saying is the interpreter is choosing one strategy, one particular strategy, whereas in many cases you could evaluate in a different order. And you could show to students that and what you get would be something like confluence. If it terminates, then you would still get the same answer. That's on a sort of possible extension, which is you could allow students to say, let's evaluate that bit first before continuing. That would no longer correspond to the launch with semantics, which has to pick one particular strategy, but it could be done because it's interactive. You could just force this little bit over there. And when we teach, we do say that, well, this is just like doing rewriting in mathematics. You can do it in any order you like. What Haskell does is do the least amount of work, so don't do work before it's actually needed to make a decision. Okay, I'm not sure if this answers your question, but...
I'm Farhad Mehta from the OST. This is really great work. I've been looking for something exactly like this. Thank you very much. My question is, I have actually two. So my first question is that, so this is not exactly Haskell, it's a subset, right? Yep. At what point do the students realize this, and does it really pain?
Yeah, I warned them right at the beginning. That's why I called it Haskellite, as a sense that it's a lighter version. it is a problem, because even though I've warned them in lectures, and I use it in lectures, that you don't have type classes, you don't do deriving show after, you can't use floats, for example. There's always some student that comes back to me with, well, why isn't this working? Yeah, the thing is, we're all programming language people. We're used to this notion of layers in languages and syntactic sugar and core and extensions. That's not a natural thing. I mean, students don't think of languages like that. So at one point, I think maybe it would actually be beneficial to accept more things in the parser and just give a message, a more directed message saying, in this interpreter, you can't actually use that, although that's suitable Haskell, for example. Yeah.
Yeah, cool. Thanks. Ah, okay. Can I ask that? Yeah. My second question is about this this pretty printing that you had. So you had the term and then the little string there, right? That's another thing that I was always failing with. When you just store the string, how do you need to actually manipulate the string depending on your manipulation of terms? How do you do this? You don't always have the same string hanging around.
Well, you just keep track of an attribute in the parser. Keep track of the lexeme that was consumed. In a parser combinator library,
Got it.
you can get access to whatever was consumed by a combinator.
Got it.
And then concatenate the thing.
And
it's
you do
really very
recursively, just
copy-pasting. It's really nothing clever.
Got it. Thank you.
Yeah, hello. I'm Jan from University of Harry Watt University in Edinburgh. And so, first of all, what are we talking today? What is amortized complexity? So if we take a simple stack data structure, we have a pointer to the top. We can only access the topmost element at any time. We can define it in Haskell. It's isomorphic to the normal list. And we will give this stack a push operation, so we can push a single element to the top of the stack. And in Haskell, this turns out to just be the LM constructor. So, but now instead of giving it just a pop operation which reverses the push, we will give it actually a multi-pop operation where you specify a k, and it will pop the top k elements from that stack. In this case, we just chose 3. Implementing that in Haskell, again, is not hard. We just recurse as long as we need to hit either an empty stack, or we are done with how many elements we wanted to pop. But let's look at the timing or the complexity of these two functions. So push is obviously constant. We are just allocating a new cell, updating some pointers. It doesn't matter how little big the rest of the stack already is. However, the worst case for multipop is that we pop the whole stack. So the worst case of multipop is O of n. However, that's a little bit silly, because after we popped all elements, we will not be able to pop all elements again. So it's technically the worst case, but if you look over like in a real execution, that doesn't really work out. So the key insight here is that, well, at some point to pop an element, we have to push it first. So instead of just looking at the single worst case for any operation, we look at over a sequence of operations and then look what will the worst case be. But important, we are still looking at the worst case. This is not like a probabilistic average case. This is still the worst case that can happen over a series of operations. So how can we reason about it? So there's 2 methods basically. There's the banker's method, and the idea here is we keep a bank account of time tokens that we can pay into in this account, or we can withdraw from the account. And so at the beginning we start with an empty stack, and our bank account is also empty. And when we push now, we not only pay, as a push we said costs 1 time unit because it's constant time, but we also make it pay an additional time unit into the bank account. So after this one push, we end up with a stack that has 1 element, but also we have now our time token saved up in our bank account. And we can repeat this a bunch of time, and this new push operation is more expensive now, but it's only a constant factor. Our push operation is still constant time. It just costs 2 instead of 1 time tokens now. But the interesting thing now is we always have as many time tokens in our bank account as there are elements on the stack. So once we do our multi-pop operation, we can use our bank account to pay for that expensive operation. So now the cost of multi-pop is amortized 0 because we pay completely from the bank account for it. So now we say, well, the worst case of multi-pop is linear, but amortized, it is constant. And that's the basic idea between an amortized analysis. Not every data structure has something like where the amortized complexity is better than the worst case complexity, but many interesting functional data structures do. So the problem with this bank account method, it's very hard to formalize because this bank account acts basically as a local state between all of these operations. So there's a better way to reason about this formally. So the idea here is we define some potential function. It will map every state of the data structure to a number, which can be anything. It usually will mean something how costly that state of the data structure will be for our operation. And then the difference in potential at every step, that will be our amortized complexity. So what does this mean? It means we will basically use this equation to calculate our amortized complexity, which is composed of the actual time it takes to do the operation. So that's 1 for the push operation in any cases, but for multi-pop it might be different. Then it's the potential after we do the operation minus the potential before we do the operation. So that's exactly this difference in potential that we will use to specify the complexity. So we define this potential function ourselves when we do the proof. There's 2 conditions on that. For any state of the data structure, we are not allowed to have a negative potential. Like the potential is always positive or 0. The other thing is an empty data structure should have the empty, like a 0 potential. Yeah. So why is this a valid way to see amortized complexity? So if you look at a sequence of operation, 1, 2, up to n, we can notice that, well, those 2 cancel out in that equation. And not only those 2, but basically all the intermediate things cancel out. So what we are left with is just all the actual time we spent on this sequence of operations, plus the final potential minus the initial potential. But as we said, by definition, the initial potential is 0, so we can get rid of that. And also we said that any potential is not negative. So this is only ever an over-approximation of the actual runtime of our system, never an under-approximation. So we can use this as an upper bound on the runtime. So we had a keynote already about this yesterday, but Liquid Haskell is a refinement type checker that allows us to specify extra properties on normal Haskell types. And it works by translating Haskell, or more specifically core, to the logic of an SMT solver, and then use that SMT solver to check those refinements. And it usually uses Z3. And for a few years now, it's implemented as a GHD type checker plugin, which makes it a lot more usable than it was before. And also nicely integrates with tooling like Haskell language server. So if we look at our definition of the stack and the multi-pop operation again, we want to prove now that this amortized complexity holds. So first of all, let's add a precondition to our multi-pop, because actually at the moment, multi-pop doesn't do the right thing. Because if you supply a negative number, which int does allow, we will just pop the whole stack, which is not what you would expect. So we specify a Liquid Haskell annotation that says, okay, we want an integer that is greater or equal to 0. We could also specify a post condition to specify functional correctness, that the list and the stack together have the length of the incoming stack, but we're not dealing with functional correctness today, we are only dealing with complexity. But now there's one issue. So for reasoning about the complexity, we will need to know how long a certain operation takes. We need this t actual. And for this, we need to derive a timing function, it's called, from our operation. And that basically follows the recursive structure of the program. So we take all the arguments of the original function and just replace the return type with an integer. And in fact, we replace it with an integer that is bigger than 0, because we always do some work. So at least we return a one-time token that it will take. And in the base cases, so if there is no function call on the right-hand side of our equality, we just replace it with a constant 1. So there's only data constructors and variables on those two right-hand sides, so that's fine. In the recursive case, we replace the recursive call by the timing function and then increment the result, so whereas do more work. This transformation could be implemented with, for example, template Haskell, or probably nicer, a GHC source plugin. However, I have not done that as part of the Perl.
What about laziness?
I mean, the laziness stays the same between both of them. So we as you see, the case match, like we only increment after evaluation. But also Liquid Haskell uses a termination checker and reasons that if the function terminates, lazy programs and strict programs result in the same result. So to actually use these later on in our proofs, we will also need to reflect them into the logic of the SMT solver. So that way we can use those functions which are more complex than measures, what Liquid Haskell automatically can use in refinements, to also be able to use arbitrary Haskell functions in refinements. However, we will have to prove any properties about these functions ourselves. So how can we prove with Liquid Haskell at all? I mean, we saw pre and post conditions, but how do we actually do proofs? Nikki and others that are in this room wrote this paper a while back, Theorem Proving for All, and it basically added a few proof combinators to Liquid Haskell that help with that. So a proof is just unit, and in fact it's unit refined with the property we want to prove. So if the property is true, it is just unit, because anything refined with true is the original type. However, if the property is not true, it's unit refined with false, which is a type error in Liquid Haskell. Also, the other bit that makes this work is this triple equalities operator. And in fact, it's the refinement on that triple equalities operator that help us with the proof, because it asserts that in the logic of the SMT solver, both arguments are the same, and it will return a third thing, which is again the same as the first two arguments. So that way we get this equality rewriting going on, because at every step where we use this equality operator, the SMT solver will check that the left and the right-hand side are really equal up to the logic of whatever logic we are working in. There's also some other helper function. I won't go into the definition in detail. This question mark operator can be used to bring facts into scope. So facts in Liquid Haskell are, again, just Haskell terms that have a refinement. So if you want to bring a refinement into scope, you can use the question mark operator with whatever term has the refinement. And triple star and QED are used to finish up a proof to make it look nice. So going back to our goal, we want to prove the amortized complexity. And as I said, we need to define a potential for our data structure that fulfills these conditions. And for our stack, we will just use the height of the stack as a potential, because the higher the stack, the more we will need to pay for multipop. That's the intuition behind that. And then our Liquid Haskell proof is just a function that returns a proof. And in this case, what should we prove? We should prove exactly the inequality or what we had before that. This equation where the timing of the operation plus the potential after the operation minus the potential before the operation is less than or equal to some constant. I chose 2. Actually, in this case, I could have chosen 1. It doesn't matter, as long as it's a constant. Proofs in Liquid Haskell we can do by pattern matching, which is the same as case matching in the proof language. So we pattern match on the 2 base cases, and we write out our left-hand side of the equality, and we will do equational rewriting steps until we are at the right-hand side of our inequality. So writing out the left-hand side, then let's remember what these definitions are for this specific case. We can substitute all of those definitions in our term. Let's evaluate second as well. These 2 potentials cancel out, so we end up with 1. 1 is indeed less than 2, so that is the proof finished. This whole process is a bit tedious because, yeah, for this base case, it's obvious that this is a constant. It just doesn't do anything interesting. So Liquid Haskell comes with something called proof by logical evaluation, and you can enable this with a flag, either in your file or in your Cabal file. And you can also use this automatic instances annotation that says basically, okay, for this specific function, which in our case is a proof, any function inside it unfolded more than once. Because what we did here, we only unfolded all our definition one level in every equational step, which is by default enabled. But if we want to unfold more than once in one step, then we need to enable this. There's also a global PLE flag which does that for all functions. But I like it to just do it for the proofs where I need it. And with that enabled, the proof is actually trivial. And as we've seen earlier, trivial is just a synonym for unit. And unit refined with true is true, but the theorem prover needs to see that indeed the refinement is true. In this case, it can do so automatically. In fact, also the other base case is trivial. And not only that, but if you specify the induction, it can also do the complicated case. But let's look at that more interesting case a bit more in detail. So as we did with at the beginning, we can write out our left-hand side and remember what all of these things are defined for these cases. Do some evaluation of one step, and now we see the ones cancel out in this equation. So let's do that. And now we're left with something that looks suspiciously like our refinement in the first place. So we have multipop of n minus 1 and the potential of, again, n minus 1 and s minus potential of s that looks exactly like our refinement where we have k be n minus 1, which is a smaller term than what we started with. So we can use a recursive call, which in Liquid Haskell amounts to induction. So we bring this induction into scope with the question mark operator by calling our recursive function and thus bringing its refinement into scope. And because this proof terminates, this is an induction, a proof by induction. So for more complicated data structures, there will be more reasoning sets. But in this simple case, as I showed earlier, Liquid Haskell can do all the reasoning except for the induction automatically. So in the actual paper, there's a little bit more I talk about. So more interesting data structures than just the simple stack. So binomial heaps are this data structure where the children are, they are ranked, and every rank has all the previous ranks as its children. And a heap is a forest of those trees, and inserting into that is also amortized constant time. And it turns out that this proof is the same proof as you would have for a simple binary counter, so where you usually just flip a 0 to a 1, but if you have all 1s, you need to flip all of them back to 0 and add a new 1 at the end. So that's the same complexity argument actually that you have for these binomial heaps. And then to go to the more complicated end of the spectrum with finger trees, cons and snock for finger trees, so adding an element on either side or removing an element on either side of a finger tree, like defined in data.seek, is constant time amortized. And so the implementation of finger trees that I chose to formalize is not actually the one from containers, but the one that was presented a few years back that is simplified. The main reason for this is that so the proof works the same way for the cons and snock case, even for the containers package. The problem is I also prove concatenation, which has logarithmic time complexity. So it also works with more interesting time complexities than just constant time. The problem with concatenation in the containers package is that it is implemented as two sets of 4 mutually recursive functions that do deep pattern matches. So they pattern match on more than one constructor level at once. Liquid Haskell needs to expand all of these pattern matches into fully disjoint pattern matches, which just blows up the number of constraints the SMT solver has to solve, which brings my PC to its knees. So the version by Kuhn doesn't have this problem, And in fact, it's very nice to implement with liquid Haskell because a lot of the internal machinery of this implementation has some pre and post conditions on the functions, which you can directly, again, specify with liquid Haskell and use those refinements then in your proofs. So that works out quite nicely. Yeah. One of the big limitations of using the physicist method is this only applies in a linear setting, and that's in the linear Haskell sense of linear. So you're not allowed to reuse intermediate data structures. The reason should be quite obvious. So if I have a stack and I multipop it, but I reuse the original stack, I can just multipop again and again and again and never pay for this expensive operation. Some data structures can exploit laziness to do so. For example, finger trees also have these complexity bound in a persistent case. So if you do reuse intermediate data structures by exploiting the memoization of laziness. However, at this very ICFP, there was a paper proposing a reverse physicist's method that could be used to deal with this issue, but that is still future work. Also, as I said, I currently don't have a way to define these timing functions automatically, but I've done some experiments, and it should be doable with, for example, a GHG source plugin. Sadly, template Haskell has some limitations that would make it very hard to do it with template Haskell, but a source plugin should work fine. Deeply nested pattern matches need to be expanded fully, which causes an explosion of constraints for the SMT solver, and depending on the complexity of the program, might be too many constraints for the SMT solver. And the last bit, when developing the proof, it's really hard to see what is an error. So if you do a small error in any of those equational steps, you will see where the error is, but the error message itself is quite inscrutable. But then looking at the equational steps again, you usually see what's going on. And the last bit, so the implementation of the binomial heap, there is a very nice implementation that uses data kinds and type families to ensure functional correctness of these these heaps, and ensure that binomial trees are really binomial trees because they have a very specific structure. However, that clashes with the refinements of liquid Haskell at the moment, but that's just an engineering problem, not a fundamental limitation. So in summary, in addition to functional correctness that we can prove with liquid Haskell, we can also prove time complexity bounds on our operations. Using the physicist method compared to the banker's method makes it easy for formalization, and this approach scales to pretty much any complicated data structure like finger trees, with the small asterisk as if it uses too many pattern matches. And as I said, future work needed for persistent data structure so that you still have these guarantees in the persistent case. Thank you.
Hi, thanks for the talk, very interesting. I wonder if you could tell us about how much cost does it have to do this kind of analysis? So you said when you try the seek, the depth seek,
yeah,
the data seek version, your PC couldn't handle it. But the case that did work with finger trees, how much memory, time does it need to actually verify something like this?
So even the simplified version, so the thing is, SMT solvers are very good at solving linear arithmetic. So plus, minus, so yep. Everything that will be a constant time is instant. So all of these examples, binomial heaps, the stack, no problem, const, snock, all are instant basically from type checking perspective. The logarithmic proof is a bit more involved and also involves nonlinear steps. So this set3 has limited support for multiplication with a constant. It does not have support for multiplication between variables, but multiplication with a constant is fine. But even then, this generates 1,800 constraints for the SMT solver, which takes about a minute and a half to type check this proof. Which is not bad in general. However, if you develop the proof, you have this 1 minute type checking time basically after like 2 steps of reasoning, and then you add another step, you check if you still are type checking, add another step, and so that slows down your development time. So I'm not actually sure if I could complete the proof for the data.seek version, because it took 5 minutes at that point to type check, and I couldn't do it.
Okay, thanks.
Hi, I'm Laura Israel from
Yeah.
Portland State University. I wanted to know if you have any data structures that you wish you could have included in your paper that didn't quite make it or it didn't work out with the system. I'd just like to hear about that.
No, not really. So I was looking for, so the thing is, this is in Haskell, so I was using for looking at functional data structures. For imperative languages, there's like growing arrays, which are a very nice amortized data structure. However, implementing them in Haskell is quite messy. So I picked from the functional subset of data structures, I picked the ones that are interesting. I thought, and I wanted something on the simple side, which is a stack, which, by the way, happens to be basically half of Okazaki's queues. And on the other side of the spectrum, I then picked finger trees because that's the most complicated functional data structure I know, and then I wanted something in the middle to balance it out. So I don't really have anything I didn't use.
Thank you.
So I guess I have two questions. The first one is, can you always define the potential just in terms of the data structure, or do you ever need to carry around like extra like meta?
No, the potential has to be defined only by the data structure. So in case of finger trees, for example, a finger tree has a digit on either side, and they can be between 1 and 4, or in the paper between 1 and 3. And the dangerous case is if they are either 1 or 3, because for 1, if you uncons, you need to recurse, and for 3, if you cons, you need to recurse. So the potential of finger trees is actually the 1 if it's either 1 or 3, and then plus the spine. So you never need to go outside the data structure, even for complicated ones.
Okay, thanks. My other question was going to be, so can this work with stref based, like if you have some impure data structure, because it sounds like the cost model is just, you just have this separate function, and that of course would be pure, even if the actual manipulation lives in ST. So would that work? Like if you wanted like some stref based union find or whatever.
I think it should work. So you just need a way to define what is the potential before and after. So but if you have like a state token, you can thread through those two executions, then I don't see a reason why not.
Thanks.
Hi, thanks for the talk. So one nice thing about refinement types, as I like to view it, is like your presentation is sort of talking about how if you have a good implementation already, you can verify that it's good. But if you have like refined types, you can also use them to prevent you from having a bad implementation. So I'm wondering if there's a way to sort of extend the work that you did or modify it such that I can ensure that when I'm writing my data structure and the operations on them, that its amortized complexity is going to meet some sort of parameters.
Well, yes and no. So you, of course, can start a proof already if your data structure is not fully implemented. However, because once you have reflect a function into the logic of the SMT solver, you need to supply the proof. So what you would end up doing is basically jumping between your implementation and the proof and updating one at a time, which is probably not the most productive way to write code. So I think this is rather useful if you write it first, then see if it has the expected one, and then possibly go back to fix stuff. I don't think it works like the other way around easily.
Okay, thank you.
I just want to ask you a bit further about your time complexity function. You kind of implied that, at least by hand, you can systematically take any function and write a sort of time complexity version of it.
Yes.
Right. But isn't that a little tricky with involving laziness? If I just say, what is the time complexity of let x equal e in blah, right, then I can't just take the time to compute e, because that x might not be fully consumed by blah.
So
and it also depends even how much is consumed by the caller of this whole function.
Yeah.
So it's a known, very tricky problem. So how does it work out so easily for you? It seems like magic.
No, so one thing is that you can just assume everything is evaluated, because we are only caring about upper bounds. So if you can prove it for these upper bounds, if you evaluate everything, then it will also hold for the lazy case.
That's a good point.
In many cases, you only care about single steps, which are by the definition you evaluate the single step, otherwise you wouldn't care about it. So usually that works out fine. And in fact, this even works out fine with higher order functions. So for the finger tree example that's in the paper, it uses, for the base cases, it uses fold L and fold R to fold cons knock over the finger tree. And even then, you can define a higher order timing function in the same way, and then have the proof work with that.
I see. So the short answer would be your systematic method just says this is going to give an upper bound, assuming strict evaluation, right? But your potential function, on the other hand, that's a purely creative thing. You, the
exactly.
the theorem prover,
Yeah.
you have to come up with that out of whole cloth.
Yes.
That's not systematic at all.
No.
That's
basically the core of the
that's
proof.
creativity.
That's basically the one thing about the proof that you need to think about, because the rest of the proof is just showing that this function is indeed the correct potential.
Yeah. Okay, thank you.
Yes, hello. I'm Niels from Kiel University, and this is joint work with Nick Wu. So, as we have learned from the keynote, creating languages can be fun. And what do you do when you create a new language? Well, you have to define the semantics of that language somehow. And as we've done in the keynote, well, as we have tried, we've tried to write an interpreter. And those interpreters usually, if you try to just do it as an initial prototype, end up being a monolithic function. And what I mean by that is not necessarily that you write just one function without a local function, but that you define your function from your AST or whatever comes out of your parser, and it returns the result of the interpreter, basically. So what we usually don't have is modularity in the components of the AST. And I think that sort of contradicts the purpose of an interpreter, because when you write a new language, you might want to experiment a bit, or you want to add some features, you want to remove something. And when you have a monolithic interpretation function, that can be a bit difficult, because every small change might affect every part of that function. So you have to change lots of small parts. And I guess some of you have already experienced that. So when you think about what an interpreter does, it basically takes an AST, so a tree with different nodes, and it assigns semantics to that tree. And that's also something that effects and handlers do, because the effects represent a tree with nodes. Then the handlers are taking parts of that tree and assign semantics to that. So I thought, why shouldn't we use effects and handlers to implement interpreters? And if you have a look at the papers around algebraic effects, you see lots of different effects. So the basic ones are like non-determinism or state, and it gets more complicated with exceptions or parallel computations. But what usually is missing is the combination of those effects. So if you get lucky, you see the well-known combination of non-determinism and state, for example. So I think it's well known then that you can get a global state or a local state depending on how you run the order of handlers. But what happens when you try to interpret a whole programming language? Obviously, you're not going to end up with only 1 or 2 or 3 effects. It's going to be a lot more, like 10. And what I wanted to try is, can we actually write 10 effects that belong to the individual language features of a language, combine that all together into a large pipeline, and end up with something that is more modular and works at least as good as writing a monolithic interpreter. And for the language I choose to try this on, I decided for Curry on one hand, because at Kiel in the PL group, we developed the language Curry. You might have heard about it. It's a functional logic programming language, but also it has some pretty cool features, which I'm going to talk about in a minute. But for the beginning, I have sort of the result, a bit of a spoiler. This is just an overview of what I ended up with. So you don't need to have a look at the specifics, but I just want to show how this thing works. So what we have here is like this snake. That's the pipeline from, this is the input of the pipeline, and this is the result of the interpreter. What we have here is this proc type that enables us to express an AST, basically. We have this thing in the middle, which is the signature, so a list of effects that we have in the AST. And then we have A, or the last parameter here, which is the result type of this particular program. And as we can see, those boxes are connected by arrows which represent handlers. So each handler is going to remove one part of the signature. So the run partial handler is going to remove partial. And then we end up with a intermediate program, basically, that has one less effect in its signature, and we augment the result type in some way. As we can see, this is not necessarily always happening. For example, if we have a look here at the runReader function, handler, sorry, we see that this doesn't change the type of the results. But obviously, it's going to change something, because if it weren't, then we wouldn't need this effect. So we can also have effects that change the result, but not necessarily the result type. And yeah, if we do this often enough, we end up with the result of the interpreter. And I'm going to get into a bit of more detail towards the end of the talk here. But I think for now, we should have a look at what Curry actually does. So Curry is basically an extension of Haskell. So we use syntax that we all know and love. So piano numbers, for example, would be defined like this, and then we can define addition on those piano numbers like we would do in Haskell. But what we can also do is that when we write a subtraction function, instead of writing another recursive function, we can reuse that add function by introducing a logic variable like from Prolog. So we if we have x and y as arguments, we can sort of write this equation that this introduced free variable z added to y should be x, and then this logic variable is also the result. So that's part of what Curry adds to the language. We also have non-determinism, and I'm going to show that in a minute. But for now, what I want to focus on is that the fusion of a lazy language with non-determinism can lead to interesting results, because usually, aside from maybe some edge cases, you're not going to be observing the sharing in the language. But here, it definitely makes a difference in the values you get. For example, here you add two independent choices. So the question mark operator is the non-determinism operator. So it makes a difference whether you add two independent choices between 0 and 1. So then you get basically 0 plus 0, 0 plus 1, 1 plus 0, and 1 plus 1. Or when you share this choice, you only get two results. Because basically, this, it's called call time choice, basically at the time of calling the plus function, you decide whether that non-deterministic choice is going to be the left branch or the right branch. And then whenever you have an occurrence of that variable, you're going to do what you decided at the time of calling the function. But obviously, because this is a lazy language, you're not actually deciding that. But it's, you're doing that just conceptually. Okay. What can we do with that? Well, we actually can desugar those logic variables into non-deterministic generator functions. So a generator function for nats would look like this, and it looks like a non-terminating function, and it actually is a non-terminating function. But what the laziness aspect of the language allows is that we can actually write basically the same as before. We just replace the free variable with this generator function. We can still use this function as before. So although we have this generator function that generates infinitely many values, the laziness will allow us to stop generating values as soon as it's obvious that this equation can't be true. Okay, so now we have the basics about curry. How do we get to the interpreter? So in my case, I'm cheating a little bit because as we saw in the keynote, writing the parser and that sort of stuff also takes time. We have the curry front end, and the curry front end takes curry code and produces an intermediate representation called flat curry. And that sort of removes all the more complicated syntax stuff. So we end up with a fairly small data type with like, I think 8 constructors, which I then divided into semantically closed subsets. So all the language features that sort of belong together, I tried to put into a subset, and that are my effects. For each of those subsets, I then defined a handler, and then I combined all those handlers into a pipeline. And to sort of give you an overview of what effects I found in the language, I have brought you on the left side the overview of the effects, and on the right side a curry program. And I'll show you which effects in the language I found, or I'll show you on the code where I found those effects. So if you are curious about what this program does, so this is the permutation sort algorithm. So the idea is when you want to sort a list, you just generate all permutations of the list non-deterministically, and then you just check all those permutations whether it's sorted. Because clearly if you are going to generate all permutations, one of them has to be sorted, right? So aside from the performance aspect of this algorithm, it uses a lot of Curry's features. Namely, it uses non-determinism. So non-determinism clearly is one of those effects that you have probably heard of if you have done anything with algebraic effects. And we have that in the Curry language with the question mark operator, the choice operator, and we also have failed down here. By the way, if you're wondering why I wrote this lat here, I just had to add that because I want to reference a lat at some point, so it doesn't make sense here, but yeah. Okay, yeah, we have state. State is a very useful effect to have, as you probably have guessed. When you're writing an interpretation function, you always have to keep track of something, mainly variables, also for renaming or for constraints. So state is an effect that I'm using often. I have the reader effect, which I'm using to insert the bodies of functions, because if you're calling a function, you have to get the body of that function from somewhere, and the reader effect takes in the program and then inserts the function bodies where it's needed. Yeah, I'm skipping the error effect because, I mean, yeah, I already put the let in here in a very, well, not required way, and I couldn't fit errors in here, so that's just for things like for the error function or undefined. I also have I/O, and that's basically for the I/O functions. And this sort of ends the category of algebraic effects. I'm going to talk about the different categories of effects in a minute, but for now, those effects which I've labeled here as algebraic are usually effects that you've already seen before, and those are effects that I've basically just reused in my interpreter. Those effects that are labeled, scoped, latent, and combined are things that I had to write specifically for Curry, although they could be reused for other languages, but I didn't find them anywhere else. So what else do we have? We have partial calls. So whenever we have higher order in the language, we're not calling a function whose name is known and that we can just look up in the program. It's going to be something that's specified by the calling function. So applying a function that is an argument to some other function, as well as supplying a function as an argument, is an effect in itself. And we also have the effect for constructing values. So we can construct literals and constructor-based values, but this also belongs into one effect with pattern matching. Because for pattern matching on a value, you need to know the head normal form of that value, so this sort of belongs together. And then we have memorization. So memorization in a lazy language like Curry or Haskell, for that matter, plays a big part, and almost every part of the language uses that to some extent. So whenever we introduce a variable, for example, in a function, in a pattern, or in a let, it's going to use memorization. And then I also have those combined effects. Combined effects aren't really a class by itself, but rather just the combination of other existing effects. And I think local bindings are used for variables. Renaming is also used for variables. And function calls is sort of a combination of all the other effects. So I didn't bother to add arrows to everything here, because in a functional language, obviously a function can do almost anything. So yeah, that's the overview. So I promised to sort of give a bit of explanation about this thing here, about these effect classes. And when we're talking about effects, often we're saying algebraic effects. And I mean, I think it's fine as a term, but it's not really true always, because not all effects are algebraic. So what algebraicity means in the context of effects is that all the nodes, or all the child nodes of a specific node, for example, the choice node here, should be treated equally when we transform the tree. And for non-determinism, this is fine, because we say we have two equal alternatives that can happen, and whatever happens, or whatever transformation we apply to this tree should happen to both parts of this node. But this is not always the case. I think the most prominent one where it isn't is the error handling effect, where you have this catch node, and we have this box here, which is supposed to be excluded from transformations done on the tree. And that's because this part, the box here, is going to flow into the tree through some handler later when the tree is handled. So we don't want to apply the transformation we're going to do twice to the continuation that we have down here. So scoped effects allow us to exclude some part from transformations to the tree, I guess. And then we have another very recent development, which are latent effects. And latent effects are basically the same thing as scoped effects, but they are a bit more flexible in the way where we can use those excluded parts of the tree. Because for scoped effects, we're always going to let this part flow back into the tree at the node, or the parent node, basically. Because as we can imagine, for error handling, the result of this part is always only going to go into this continuation, because it doesn't make any sense to move this part to any other catch, because it's specific to this one. But for latent effects, for example, for the memorization, it could be that the argument that we're memorizing here is only evaluated later. at some other point in the tree, or it might be that it's not even evaluated at all. So latent effects allow us to delay this evaluation here indefinitely and to do it at arbitrary points in the tree, basically. Okay, if this was a bit too abstract for you, I've also have an alternative explanation. So basically, the algebraic effects are the good old USB port. It has like full context, and yeah, it's very simple. Scoped effects sort of add a bit of capability to that, but it's sort of still the same, the same plug. And then we have latent effects with this sort of very strange connector here, and I'm not sure whether everyone in the room has seen it before. But we've seen that in the language here, we have all those aspects. And we sort of need to plug them into the same system. And how can we do that? Yeah, well, adapters is a great solution to that. There's this wonderful paper by Berthe van den Berg and Tom Schrijvers called A Framework for Higher Order Effects and Handlers that solves exactly this issue. So basically, we just pick one universal interface, and then we use adapters to plug all our effects into the system. And this allows us to have the simplicity, for example, of algebraic effects, where we can use it, but we also have the complexity of latent effects where we need it. And it also allows us to let the effects, well, we have to do some changes, but we can largely keep the effects as they are. All right, so I'm going to give a quick overview of how the handlers look in my pipeline, but I'm not going to show too much code. What we have here are the actual types in my program. So we already saw the proc before, and we also have seen this A here. But what's a bit different in reality is this part in the middle here. In the paper by Van den Berg and Tom Schrijvers, they're using only a more general signature, but I found in order to have modular handlers in the sense that you can combine all kinds of handlers, so for algebraic, scoped, and latent effects, you need to sort of be a bit more concrete about your signature. So what I've done is I've split the signature into 3 different parts. So algebraic effects go into this signature, scoped effects and latent effects go into those 2. And then we also have this mysterious L parameter, which is due to the latent effects. And what a handler does in the situation is it takes a program where, for example, if you want to handle the non-determinism, it takes the non-determinism out of the algebraic effects signature. It adds some kind of semantic functor to the result. So we have the list functor here. And what it also does, due to the latent effects, we have to keep track of the semantics functor in this separate L argument here. And that's basically just the list transformer, I guess, but with the arguments flipped. So the L is not around the list, but inside. We can also do the same for scoped effects. So we can have one part algebraic and one part scoped, or we can do this for latent effects. So then we have something in the latent effects signature, and we're not necessarily adding modifying the result type as I said before. So with all those handlers, I'm also showing the handling pipeline in actual Haskell code. And what we can see here, we're taking a list of, well, programs in, and this proc is the name expression would be more accurate, I think. But to handle that, we're running all those handlers in sequence, basically. Okay, so that's what I've done, and for the evaluation part of the talk, so what this approach gives me obviously is flexibility, because I have this pipeline and I'm free to reorder all those handlers in an arbitrary way. And what this allows me is, for example, if I run lazy first and then run ND, I'm going to get the call time choice semantics I mentioned earlier. But if I just switch those two handlers around, I'm going to get a runtime choice. So something that would be probably a change that would need a significant amount of work in a monolithic interpreter is just switching 2 lines of code here. And I can also have 2 pipelines or more of them in parallel without duplicating code. What I can also do very simply is to extend the interpreter. So after analyzing the specification, I just have to add effects if necessary, write the smart constructors, and then adapt things in effects that are affected by the change. So here I did a small case study for adding logical unification, and it turned out I already have 3 effects that I needed for that. I needed to define 1 new effect for having a constraint store, but that's also just an instance of a state, so I had that as well. So realistically, I just had to define the smart constructors that implement the unification logic, and I had to adapt a bit of the pattern matching, because now I could also pattern match on 3 variables. So I had to just modify the parts that were interacting with this unification, but the rest could stay the same. And also, I quickly had a look at the performance. As you can imagine, having multiple handlers run in a pipeline means that I'm traversing the tree multiple times. You can do something like Fusion for free to fuse that into a single pipeline, and this gives a considerable speed up, ranging from, I think, like 1.3 to 23 with an average of around 3. So that's not necessarily a problem. All right, to conclude, I found that effects and handlers provide modular semantics, which I found to improve the flexibility, the reusability, and the extensibility of my interpreter. I'm forced to make explicit design decisions, for example, the order of the handlers, which is also going to influence the result. And this even works for more complex combinations of effects. But what I've also learned from this whole process is that the accessibility of non-algebraic effects could be definitely improved, and also that the fragmentation of the different effect frameworks makes this whole process quite difficult. Okay, I've not really shown too much code in this presentation, but obviously that code exists. So if you want, have a look at the GitHub repository or the paper for explanations and for the full code. Thanks.
Do you mind going back to when you introduced the question mark operator? That's in the first, third part of your talk. So yes, this one here.
Yes.
So the let on the left is basically an effectful bind. In Haskell, we will express it using do notation. So do you have a universal bind in Curry? Where that let would basically give you the same value as the first line, the first expression.
Do you mean whether in Curry whether we have a let that gives the result of the first?
Yes, that's right.
Well, I guess it depends on the value you have here. If, for example, this was a closure, then you would get this result here. Or
I have to repeat myself. So basically, that let there, in Haskell,
yes,
right? That's an effectful bind, but which we use a left arrow. Now, as you know, in Haskell, there is this so-called universal bind, which we just use the let keyword for. So in Curry, do you have a universal let?
From your explanation, I don't think so, but I think we should talk about this later.
Hi,
Hi.
Casper Bak-Paulsen, TU Delft. Very cool work. I actually had two questions. First one is, you sort of touched upon the fact that when you permute the handlers, you get different interactions, right?
Yes.
Is that the only place where you get interaction? You mentioned that it was between lazy and, I think, non-determinism.
There are other places where things interact. Where is for example, I think that, every handler that produces a semantics functor is going to interact with the other handlers. So this order of effects, of effect handlers here, I chose due to how I want the semantics to be. For example, I want either an arrow or a list of results, basically. You could also switch the order. Then you could have a list of errors, for example. So all of those things interact in some way. I think the handlers that produce some part of this result here are fairly fixed due to what you want in the result. But there are also handlers like the reader, for example, here, which you can, I think, arbitrarily position in your pipeline without really having too much of a difference.
Okay, thanks. Second short question. Have you thought about equations? That's one of the things that algebraic effects provide. Have you thought about it? Do you get an equational specification from this?
Equations?
Yes, equations for your effects.
Oh, so you mean specification?
Yeah.
Yeah, I've not really, those handlers don't really produce them, but I think it would be an interesting thing to have a look at for the interaction of those handlers, yes.
Hi, I'm Grant Van Dommelen, Portland State University. I was wondering, you mentioned the accessibility and like the fragmentation of effect frameworks. What did you use when implementing this, and what challenges did you find with them?
Yeah, I basically ran my own, which is it's not the best answer, but I think due to the relatively recent developments around latent effects, none of the existing frameworks explicitly promise that they are capable of doing that. And I found during the development, whenever you have some strange issues or a problem in general, it's always easier to have your own code base to have a look where things go wrong. But ideally, a good framework is going to solve many problems. So that's definitely something that's desirable.
Okay, thank you.
mobile microphone.
Oh, so we're going to have, we're going to use two microphones for the audience and one for the...
Okay, but you're fine. I mean, you can...
I'm going to just carry this around.
Okay.
No.
All right, everyone, welcome back to the afternoon session of the 2024 Haskell Symposium. Hey, if you haven't signed up for a lightning talk, there's Google Doc. You could do that. Whilst you're doing that, though, we'll hear about the state of GHC, and Simon Peyton-Jones needs no introduction.
Okay, thanks. So this is going to be very sort of interactive, I hope, not just a monologue, because I feel as if I'm speaking on behalf of a small army of people who've done all the heavy lifting, and I just sort of run around tying up loose ends. So please feel free to intervene. Now there's a microphone here. There's one here, and just sort of maybe just sort of hand it around, so you don't have to physically come up, you can just grab it. So maybe, Pablo, would you, Pedro, sorry, would you just keep an eye on everybody and throw the microphone to them? It'd be much more fun. But the reason for microphone is not so much to be heard in the room, but because remote participants won't hear us at all if we're not using the microphone. So it's polite to them, okay? Where are we in GHC land at the moment? Well, let's start with the releases of GHC that have happened this year. Just to remind you, there is now a the GHC status page that's meant to tell you an up-to-date story about what releases are happening and what releases are planned. So, and it really, last edited by Zubin a week ago, this is actively maintained. And up here, you'll see in the sort of, there's a row here for each release. And in the column next planned release, these little links here go to the milestones for those release, and the dates for the release are on the milestones. You have to follow one more link to find anything about dates and schedules. Okay? Let's see. So here's our current story about releases. There's a 9.6 seems to be a fairly stable iteration of GHC. So we released 9.6.6 in July, and I think, tell me if I'm wrong, anybody, I think we're planning to continue to, this is in a pretty stable state, but I think we're planning to continue to support that, unlike 9.8, which turned out to be a bit wobbly and was rapidly overtaken by 9.10. Zubin.
There might be one more 9.8 release, but not too many.
Okay. So it might be one more 9.8, but sort of 9.8, don't leap to 9.8 unless it's a stepping stone to somewhere else. 9.6, you should be fairly safe, is that right? Yeah, okay, good, thank you, Zubin. 9.10 actually came out in May, so I'm going to tell you a little bit about what's in that. A 9.12, we're planning to forking the tree soon, like in September, and planning to make a release in November or thereabouts. I'm going to tell you a bit about what's going to be in that as well. So that's the sort of plan for the release schedule. Still currently 2 a year, and we're trying to be transparent about which ones we're then thinking, okay, we're not going to keep patching that. The trouble is we can't maintain too many active branches at a time. There just isn't a sort of maintenance, it's a maintenance burden to make releases. So I was trying to be clear about what we're not doing. Okay? So let's see. So new in 9.8 stroke 9.10 because both 9.8 and 9.10 come out since last year, right? So essentially, these are the kind of the biggest new features in the last 12 months since the last Haskell implementers meeting. So what's this? Quite a lot of all of the 9.8 and 9.10 stuff is really to do with consolidation, I think. It's sort of filling out the design envelope of what Haskell is to make, to fill out design corners that were sort of not quite there. So this visible for all thing is one of them. This is sort of, it's moving in the direction of dependently typed languages, but without moving to full spectrum dependency. So GHC still has a complete phase separation. There's no doubt about which are type parameters and which are term parameters, but there's a bit more syntactic flexibility about what you can say where. So, have you all seen this? You can now say in a type signature for a function, you can say for all a arrow AROA instead of for all a dot AROA. And what difference does that make? If you're in the core language, it doesn't make any difference at all. It's still just an ordinary L for all, really. But the difference is in the source language that you now, at a call of this function RID, you must supply a type argument. It's like as visible an argument as any of the term arguments. So here's a call of RID, and you apply it to a type, in this case, with no funny @ sign, right? It's not optional. It's a compulsory parameter, like any value parameter. Must be there, okay? In pattern matching, you can pattern match on T as well in the left-hand side of the function, if you want. So Here you can see that here I'm applying RID impredicatively to a polymorphic type. So you can already tell that, hang on just a second, but you can already tell that when the parser and the renamer are looking at this, they're looking at int and for all A or OA. And at the moment, the parser thinks that looks like a term to me. So we have to embed for all into terms to begin with. And later on, when the type checker gets to it, it says, I know the type of RID. This is really a for all. So this first argument must be a type. And it sort of walks over it and checks that it doesn't contain case expressions or something. Yes?
I'm mostly wondering what the lambda syntax is. Will this be big lambda, so / //?
We're going to get to the lambda syntax is where's the lambda syntax here?
Oh, okay, /
right?
at. All right, thanks.
So you say, so yes, if you want to, instead of doing this on the left-hand side here, you can do it on the inner lambda, and it is lambda with an at. And there's a little thing here. If you write lambda at without a space, that's some kind of operator. You have to put a space. I hate that. So put a space there. It's a safe thing to do. I don't know. Maybe in the end we'll take that out. So I feel as if that's a little glitch, really. Okay. What haven't I said about this? No, I think, and why is this useful? Well, because for some functions, you know that there are lots of functions that have proxy in their type, right? Why is that proxy there? Is because the author of the function wanted to say, you must supply a type argument, right? I'll call it proxy. So any function with a proxy in its type is a candidate for doing this. And sizeof here is a good example. Sizeof has type, now for all a arrow, this is a type class size a to int, and you say size of float. What could be more natural than that? Rather than say size of open paren proxy : float, or : proxy float, or proxy at float, or something. Much better. Okay? So, so this part is called required type arguments, and these being able to explicitly abstract. Beg your pardon. This part is called required type arguments. Yes. Oh, and I beg your pardon. If now I'm hesitating. If something has a for all type, you don't need the little at, Christian, right? But for ordinary, for all dots, right, you can still write. So here is HR with this type abstraction things. HR has a higher rank argument, right, a polymorphic typed argument. And in its argument, you can now explicitly, just like in the lambda calculus, you can abstract over the type argument. Optionally, you don't have to. You can still just say lambda x's. But if you want to have this optional big lambda, you can. And it's useful because it lets you bring A into scope, right? And here it is being used in the right-hand side. Does that make sense? And so at the moment, in Haskell of yore, Haskell of last year or the year before, often the only way to bring type variables into scope was to use a type signature, and for all variables of the type signature, scope over the body of the definition, right? But we always knew that was a bit weird, right? Because the type signature could be somewhere else in the module, right? It doesn't even have to be adjacent. And moreover, it doesn't work very well for things like this higher ranked argument, right, where there isn't a type signature at all. So these two, and the last thing is you can do the very same in, as well as the lambdas, you can do it in definitions. This is for all dot, and you use ID at, and in type declarations as well. And sometimes you want to say for all k, and in the type declarations you data t of kind k. Does that make sense? This is all, I see this as all as exploring at something that in principle is not at all difficult. All of these things are there anyway in the core language, right? It's just that in the source language we want to make it possible for you to write them without making it, unbearably cluttersome to be forced to write them all the time. So there's a lot of somewhat ad hoc decisions in this design, but they seem to be working out fairly well. Any observations or questions about this? Andres.
Just a side question about it. Like, if I have scope type variables enabled, then in ID I would already have A as a type variable in scope, right? And now, with the at A, will I get a warning that I'm doing type variable shadowing? Or
honestly, I'm not quite sure. I think you'd probably get a shadowing warning. That's a good question. Yeah.
Or is that a special
You certainly
case?
don't use the, I mean, you could say be there perfectly. That would be absolutely fine. But I think if you're using extended for all scope, which is what the for all thing is called, extended for all scope and type abstractions, you probably should get a shadowing warning. You should give it a try.
Okay.
I'm not quite sure, but we now do have two slightly mutually redundant ways of bringing a type variable into scope. But this one, as it were, is the sort of, like, this is the way God intended, I feel, as if, you know. Yes, but type inference does not work with these guys, right? So this is good if you know what the type of the argument is, because it comes from the function. But don't expect to just write for alls and write big lambdas and expect them to infer really well. Yeah.
How does this feature interact with GADTs? I mean, consider a function which says which has for all a row and then big X of a, when big X is actually a GADT, for instance, indexed by a list of a's. I mean, I pattern match on the constructor of X, and can I write the pattern of that? It's a list of some a in the left-hand side of this explicit for all?
I don't think I have the program you just described clearly enough in my head now. I think we need a bit of paper. But I don't think there's a difficult interaction with GADTs here.
Okay, so
there is a question about scoped, how are type variables brought into scope by patterns in pattern matching on constructors, right? And that's a whole nother story, which I think hasn't changed very much in this, but I think we may be changing a little bit in the future. Has it changed very much in this? I don't think so. Not by these two features anyway. Yep.
Yeah, so, you know, it's maybe my problem, but if you put a typed hole where it expects a type parameter, what will it do?
So say that once again?
So if you put a typed hole where you would say, you know, int, or, you know, if I say size of underscore.
Oh, I see. Size of, yes, you could say, I think you could say size of, you can certainly say size of, you can certainly use, like in type applications like here, you can certainly say at underscore, meaning at, you know, some type. That's quite useful when you want to omit one of these positional arguments. I'm hesitating slightly for, could you say RID of underscore? I think so, actually.
Okay, because we have partial type signatures that kind of, okay, but interesting.
But then, though, and typically, it would be a bad idea because probably, like in this size of, if you say size of underscore, you're back into the original problem about ambiguity, right? But I'm not 100% sure, but I think so. Yep. Okay. Yep. Please.
You give the example of size of as a good candidate. Do you think that that will ever be part of base, one of these functions that does have the explicit?
So then there's a whole, that gets into a question about stability, doesn't it? So over time, you'd like to move the API of, well, all libraries, right? Any library that is using proxy at the moment might well want to shift to this. And how do you do that in a way that is, goes with the flow of users? One thing, I'm going to talk about stability a bit later, but yeah.
Just in response to Maddie, I think we've made a small design mistake in using underscore both for whole and for thing I wish GHC to infer, and maybe one of them should move.
Well, you have a whole proposal about that, don't you?
I have a whole proposal about something in this space that I haven't looked at in 2 years and probably should be revised.
Somebody else, yes, here.
For this visible for all, did you say you could match on the type parameter? And
No.
could you? Okay.
Sorry. So I meant when I said you can match on this T here, you can't say RID of int this and RID of bool that. No. Right? We're not, we're not passing representatives that we can look at. It's all going to be erased. So it ends up having to be a type variable. Thank you. Good point. What? It would be nice, but it wouldn't. But then you'll be going. Now you go to typable, but then you can match on typables. All right. Yeah. And so maybe you want better syntax for matching on things with typable constraints. Write a GHC proposal, but not in 9.12 or 9.10 or 9.8. Right? Yeah, but once you got a typable constraint, you ought to be able to do. You can do all of that, but it's a bit clumsy, and maybe a bit better syntax. Yeah, please. Oh, go ahead. Thanks.
So does it only work for types, or can I use it also for any kinds? Does it lift to the kind level as well?
Oh, yes, all of these can be kinds as well. Yes, absolutely. Yes. Types and kinds, they're all the same thing. Have been for some time. Thanks to Richard and Stephanie. that's fine. We've got, in fact, today I saw, Ed showed me a program in which he actually uses the same thing as a type and as a kind. Scary. I mean, there's a lot of unsafe coerce in the same module. So. Okay. Another big new thing in, that I don't know, does anybody know about this exception backtrace stuff that Ben has spent so much time implementing this year in any detail? So, I mean, in GHC, if you call error, then, that makes an exception, and then, the program falls over and just says, error, bad thing happened. But you'd like to know, error, bad thing happened at this place in the program, with this call stack or something. The trouble is we have 4 different ways of collecting call stacks or gathering backtraces, and this exception proposal not only lets you choose which way you'd like to use, but also lets you attach user-defined metadata to an exception. So it gives you much richer information about where exceptions were thrown from. It's quite an elaborate proposal. It spent a long time in the making, but it's actually part of 9.10, I think, isn't that right? Yeah. So Ben Gamara is the person who put most work into this, spent a lot of time implementing, so thank you, Ben. I think this will really help in, when the system falls over, it's terribly upsetting just to say head of the empty list somewhere in your program, right? No, Leonard, yeah. Oh, yeah, behind you.
Is there a runtime cost?
Oh, all of these things have different runtime costs. That's why there are 4 of them, right? Or maybe it's a trade-off between cost and information. I think one of them is just walk the Haskell stack and tell me, right? That has no runtime cost, but is a bit weird because it follows the path of lazy evaluation. Or there's, Haskell stack, which does have some runtime cost, but gives you something much more sensible. So you have to choose, sorry.
Sorry, just
a
question about runtime cost. So the performance, if the exception does not happen, is unchanged, right?
No, for some of these mechanisms, like the Haskell stack mechanism, there is a little bit of runtime cost regardless of whether an exception is thrown or not. Right?
So if I write an exception, raise exception somewhere, so it has a runtime cost.
No, I think only if you say use this more costly mechanism. I think the baseline case is probably still just like today. You don't get very much information, but you don't pay anything. But you can sign up to paying more and getting more.
Thank you.
Christian?
I guess I can't take the whole hand and abstract over the mechanism. I have to decide at implementation, at where I call error, which method I want to use.
Actually, I don't know. Yeah, Zubin may know. Now you're exceeding my knowledge base.
It's in your main function or anywhere in I/O, you can enable particular backtrace mechanisms.
It's a side-effecting I/O operation, is it?
Yeah, it's side-effecting I/O operation.
So you just say at the beginning of your program, use this mechanism.
And you can enable and disable them dynamically. And so with Haskell stack, whether it gets printed or not, you can choose, but you have to pay for the runtime cost of the extra arguments, whether you enable it or not.
By the way, I love the Haskell stack thing because I don't know whether any of you guys use it. I use it all the time now because it lets you, it's sort of incremental. You can just say, give me a couple of call functions. It doesn't have to be everything. It's not a global flag. You can just add it.
I would like a flag that says, put Haskell stack on everything.
That would be cool, actually, yes. Everything in this module, or just everything?
Everything. So when you're debugging and you find something, I don't want to go in and modify a bit here and there and there. Just sort of
I
bang.
have a bit of CPP that says, has debug call stack, and it turns into nothing, or into, yes. Okay, good. So this is big. Then there are some smaller things that have happened, like extended literals. This is to do with just being able to write int 8 literals or int 16 literals. There's a little bit of this. All of these, by the way, GHC proposals. I've been putting the numbers in them mostly. I should have put the number for this one, but the process is actually working. We're getting proposals and implementing them, and they get put in. So this is literals for some of these a richer variety of base types. Deprecated instances allows you to say, you shouldn't be using this instance, right? But the deprecation message comes out if the instance is ever used. So it means that there's a path that says, I intend to remove this instance. You can release a library which deprecates it, and people will be told, oh, it's going to go away. It gives them a little bit more time But the nice thing is it comes out when it is used. That's why it needed a bit of compiler support. There's a bit of, this is me failing to edit the slide. Bit of the namespace stuff is about when you declare the fixity of a symbol, you can say infix L, 6 plus. But did you mean the plus at the term level or the plus at the type level? Or if it's capital K, did you mean the type constructor K or the term constructor K? For a long time, it's just meant, it's tough, you just mean both. Now you can say infix L8 type K or infix L term K. Data K, you say. So, and similarly, when you're deprecating things, you can say whether you're deprecating the type version or the term version. It's all because of the punning that we have and use so extensively, right, at both the term level, that the same symbol appears in both terms and types, right? Such a good idea, such a bad idea. I don't know which, but this proposal, several proposals, and now I think this is now pretty consistently implemented, just lets you say which you mean, if you mean one or the other. Okay? Good. So those are the things that are in the releases you can get today. But the upcoming fork, and therefore the thing we're working on now, what's come since 9.10, all patterns. So this again was a GHC proposal, which Sebastian Graf and David Konther and Ober wrote. These are all patterns that don't bind variables. In the end, the steering committee pulled back from saying, can you have an all pattern that binds multiple variables? These are ones that do not bind any variables. So here, if you've got this enumeration type, you can match on red or pink, and here match on blue or purple. That's quite convenient sometimes. Not very hard to design, not very hard to implement. Took a surprising amount of hoo-ha to get the proposal decided, partly because there is a design space here. Multi-line string literals, this Brandon Chin. Brandon Chin isn't here, is he? I'm not sure I've ever met Brandon Chin in person, but they're very thoughtful and quick off the mark, and has implemented this multi-line string proposal. It just lets you write. You have to start with, I think, 3 quotes and then write a whole pile of stuff. So it's a way of incorporating whole documents inside GHC programs without much trouble. Just one sort of thing you think, yes, convenient, but nobody's ever done it. Now they have.
Yeah, so Simon, so all patterns, do they only work on enumerations, or are they going to work on arbitrary patterns?
All patterns will work on, you can take the ORs of any patterns that do not bind variables. So they can be, you could say just open curly brace, close curly brace, vertical bar, blah, or just underscore. That's fine to put in an OR pattern. But you can't say, C of X or K of X, right? Even if the X's are the same. Yes. Right. Okay, yeah.
Sorry. Could you please tell me, why couldn't you choose vertical bar?
Of course, that was the longest part of the all pattern proposal, is what syntax to use, right? Why don't we use vertical bar? I have forgotten, but there was very good reasons for it. What? So we're using semicolon, yeah, but why not vertical bar? I mean, all patterns, you'd think vertical bar, surely, right? Okay, you should go and look at the proposal. There was a long discussion about this. There were multiple votes. There were, people died in the trenches. Small children were sacrificed on the altar. It was. Okay.
It came out wrong anyway.
That's right. These are the things you cannot get right. Let's see. Overloaded, records and overloaded dots. So in the end, we sort of converged around this type class has field for overloaded records. So now you can say, but previously, you could only say x dot f, where f is a field of a record, if the field had a lifted type, like int or maybe. Now you can say x dot f, where the field has an unlifted type, like int hash. So this is in effect, the type class itself has become representation polymorphic here, because the A here can be a representation polymorphic type. So it just expands the scope of what you can do with Haskell. There's a bit more in this proposal as well, actually, that's also implemented as well. So here, u.f, then I'm using int hash arithmetic on it. Does that make sense? This is, again, is filling out the envelope, going a little bit further.
Sorry. Oh, yeah. Why do you need that equality constraint on it instead of just substitute that A with the int hash?
Oh, yes. Why don't we say has field fu int hash? Well, we could maybe do it with functional dependencies, but the trouble is typically when you're doing type inference, you don't know what A is yet. And so you're trying to figure out what A is, and the way you figure out is you say, well, I can match on the F and the U. I know it's a record of type U. I know it's a field F. And A will match anything, so that's good. And then you say, oh, and now I need that A must be int hash. So it's a sort of way of staging type inference, really. It's to help the inference engine is perhaps the best way to say it. If you weren't bothering with, if you didn't need to do type inference, then you could just have put an int hash there. Okay? All good? Let's see. Oh, what else? This is a little piece. Remember those required type arguments? We said that, so now we've got to have types, things that look rather like types, but they're living in the middle of terms. In 9.10, you can't write this. I said you could, but it's not true. You have to wait for 9.12, because we have to extend the parser a bit, the term parser, to understand for alls in terms, and only later in the type checker do we convert that term into a type. So that part is only here. Okay. All of this stuff to do with required type arguments is done by Vlad and Andre, who work for Seracul, and they are amazing pair. They really work hard on our collective behalf. We should they're not here, but we should give them a big thank you. I think they've been doing a lot in this filling out the corner space. Okay, where are we? Oh, a pet favorite of mine. So mostly I've been running around doing code review for all of these things. But this is something I've actually done myself, which finally, this is a proposal that Richard and I wrote about that says, at the moment today, you can set for a type class overloaded function, you can say specialize f int arrow bool arrow int. I should have written this out. That's today's syntax, right? But here's another way that you might reasonably want to write it. Just specialize f at int, right? Because you could write that at a call site. And after that, there's no real reason you wanted to write out the whole of F's signature, right, with int instead of A. You really just wanted to say the int instance, please specialize F for that instance. And then once you've got that far, you might want to say, oh, look, and I'd like you to specialize it also the case for the second argument is true. What's the big deal, right? We're specializing it for the int type and therefore the int dictionary, but also for the true argument. Right, so this syntax just lets you write out a little, as it were, prototype call to F with some for alls here to say specialize this for any value of X, but only for the case when the type argument is int and this term argument is true. Then take the whole right-hand side of F and just fill in all those things and compile it. And then anytime you see a call to F that looks like that, you can replace it with that new function. Yes.
Yeah, it should be an F in the first definition, right? Just checking. The first one should be F.
No, definitely not. Shouldn't be an F at all. Yes, of course it should be an F. Thank you very much. That is horrendous.
Does it specialize it only when you have an actual true in your source code, or does it dynamically at runtime decides if it's true, then I'm going to use this other function?
So when you write this pragma, it will create the specialized version, right?
Yes.
And then it will also create a rewrite rule that says if during simplification you ever see that pattern, replace it.
But it's static, it's not dynamic. If I call f at some point...
Yes, it's completely static, yes. It does not, f itself does not say, oh, is the argument true? If so, zoom off to this guy. It does not, no. Because, of course, inside f, it's going to be testing that anyhow. But it might still, yeah. You could imagine doing that, but I'm not at the moment. But feel free. Yaro?
Does this use the new higher order rewrite rules in the rewrite rules that it generates? If you have like
it doesn't use higher order rewrite rules at the moment, no. But I think if you had an argument that maybe you're asking, if you had an argument that was a function,
yeah,
right? So you said f at int xg, right? Then it would specialize just when you called it on g.
But I mean, if you call this on a, or if you write instead of true lambda x of g of x or something
yes.
like
That's a good question. I don't know, maybe with the, this is a self-interested question, as Yao's implemented this, the talk you're going to hear tomorrow from Yao is about higher order rules, and that might actually help here. Yeah, I hadn't thought about that. But.
Cool.
So this is implemented, there's a branch with this, but it hasn't landed yet. And so the question is, it's a race for whether I have enough cycles to land it before 9.12 gets forked. But I find myself quite a lot writing functions, and I want to write them once, but I then want to be completely confident that I'm going to get, the version specialized for true and the version specialized for false with no runtime tests. And this lets you be completely confident. Okay, where are we? So a few other smaller things in 9.12. Dropping support for 32-bit macOS. Why are we dropping that? It's because nobody uses it or something?
Yeah, I don't think anyone uses it. And
probably find 5 people here who say
and no one maintains it, and we don't have the CI resources to test it, so might as well get rid of code that no one's testing or using.
And on the profiling front, I think I'm probably understating things here by just saying profiling works for dynamically linked code. There's been quite a lot of other work on profiling, hasn't there? Do you know anything about it?
There were late call centers in one of 9.8 or 9.10, I think, which allow...
Late cost center call centers, is that? So late cost centers means, let's see. Do you know about cost center profiling? That's where you say set cost center, SCC, the SCC pragma, and it gives you, this goes right back to the paper that I wrote with Patrick Sampson 20 years ago, but it gives you sort of lexically scoped cost centers. It's all very beautiful and nice, but it does inhibit optimization. So late cost center says, do all the optimization pipeline stuff, and then add these cost centers into the code. So it gets in the way of optimization much less.
Yep. That does mean you have less useful names for the cost centers, because names are generated by GHC. So whatever it comes up with is what you get. So you might have to look at the core to interpret your profiles.
What this cost center means, yes. Okay, and deterministic object code generation, this is, I think, some fairly big users of Haskell are very keen, particularly with sophisticated build systems, on having deterministic object code. And I think Rodrigo is working hard on this at the moment, isn't he? So, okay. Now, Cheng, where's Cheng? WebAssembly. So yes, you probably know that you can compile now to WebAssembly. Pretty good.
Yeah, right. So back in 9.6, we merged the initial version of the GHC WebAssembly backend. That means you can compile your Haskell code to a self-contained WebAssembly module that runs everywhere, including web browsers and stuff. And for the progress in 9.10, we added the JavaScript FFI extension. So that means that you can write foreign import JavaScript plus a little bit of JavaScript snippet code, and that will enable you to call into JavaScript code directly in Haskell without you needing to write any of the glue code. And it allows you to call JavaScript in Haskell, and it also allows you to export Haskell functions as JavaScript functions. And the best part is that it integrates the Haskell concurrency model with the Haskell green threading model, so that you can have like calling the JavaScript async functions like fetch, and then the Haskell thread will block until the promise resolves or rejects, but the entire runtime is not blocked. You can also have the Haskell runtime schedule other Haskell threads for execution. So that is the JavaScript FFI feature added in 9.10, which I will give a detailed talk about it tomorrow. And the next to come one is template Haskell support. I promised a lot of people I'm going to be delivering template Haskell in like Q3 or whatsoever, but it is a very soul-grinding task because dynamic code loading in WebAssembly is pretty hard, and I've been bothered with some memory leak issues. So I'm almost there. Cannot give exact ETA yet, but I hope template Haskell can be fully delivered before the end of this year. And after that, I'm going to be implement multi-core parallelism. That basically means porting the threaded runtime of GHC to WebAssembly so that you can have one Haskell app in your browser eating up all your CPUs and CPU cores. And I hope it's for some better purpose than crypto mining or whatsoever. So yeah.
Amazing. On my laptop, Firefox already eats up all my CPU. So Cheng, is it still true though that what I wrote here, that it's still a tech preview in the sense that it doesn't come in the box? You have to build yourself GHC in a particular way to get this?
So yes, this is, because GHC is not fully runtime retargetable yet, if you want to cross-compile Haskell code to a special target, then you have to compile a special GHC for that purpose. But if you're going to be trying the GHC WebAssembly backend, then we have the CI artifacts that you can just download and reuse all of that. And we also have detailed setup instructions on how to use those binary artifacts, which I will also give a talk about it tomorrow.
So we want to make it more retargetable. Yes. And that's another thread of work that is going on somewhere, isn't it?
Exactly. I'm not too well versed in WebAssembly, but do you support dynamically linked libraries in WebAssembly, or do you build one big binary? Is it basically all statically linked?
Sorry, can you repeat your question?
Is the final binary that you build, is that a completely statically linked thing, or do you have?
Yeah, it's completely statically linked with all of your libc and whatsoever bundled in the WASM module.
So we can't yet compile GHC with plugins that run in the browser?
Plugins is a whole another story. I think Laut will give you a much better explanation because he is working on.
But without plugins, we could run GHC in the browser?
Unfortunately, the question is hard to know for now due to a lot of technical reasons.
Right.
Oh, I've just spotted Andreas sitting quietly at the back here. the grandfather and curator of WebAssembly. Thank you so much. Who else? Anybody else want to say anything about WebAssembly? Okay, so Loiter. Where's Loiter gone? Oh, where's he? Oh, there. Right. Yes. So JavaScript.
Yes, we don't have multi-core, but we can load dynamically things more easily. We've done a bit of work on it. Most of our work has been maintaining and bug fixing and small things, but some new features. GHC used to have an optimizer, which was based on abstract interpretation of JavaScript AST thing, which is about as easy and fun as it sounds. So I didn't want to replicate that in GHC, and so we have a much simpler optimizer that works almost as good, but it does not use fixed point iteration or anything. It's simple and it's much less buggy. And also, if you have C sources in your Cabal packages, they will get automatically included in your build artifacts that you get out of the JavaScript backend. Still, because the JavaScript backend targets everything running in the JavaScript managed heap, and etc., the representation of pointers is a little bit different. So what happens is if you use C sources, you get something you can call from JavaScript, but you have to write a small glue function yourself. And the glue function will basically be a no-op if it's an int-to-int function. But if there's something with pointers or arrays, then you probably have to copy a little bit of data. And that's pretty much it. That makes it a lot easier. And the other thing, we have now support for Google Closure Compiler again, which gets your JavaScript code a lot smaller than before. So with the optimizer in GHC and the Closure Compiler combined, it's basically back to almost where GHC used to be. And that's pretty much it for the JavaScript backend. Next slide. And another thing that I wanted to say, please try it, is that we now have a RISC-V native code generator. This was written mostly by Sven Tenney, and he's a new contributor to GHC. And Moritz wanted to say that it's a really nice project that we can have a new contributor and make something big or something quite very usable. RISC-V is still a bit up and coming, but I think we'll see more of these things. So it's currently in the GHC master RISC-V branch or something. You can find it on GitLab. But it's close to be merged. I hope it will be in 9.12, but I'm not completely sure yet. It passed the test, so yep. Oh yeah, the names are there. Sven did most of the writing, and Moritz, who's done the ARM64 for Apple and that kind of things, he's done some mentoring.
Yeah, so it's quite a lot of work on back-end stuff happened on GHC this year to make it run on different platforms. Fantastic. Okay. Now, what else is happening? So I just left a little space here because I'm expecting that some of you are working on things that you can tell us about. Anybody got anything they've been working on? At all? I'm shocked.
So this is very much in the very initial stages, but right now you might, if you're using plugins in template Haskell, so GHC only has one notion of dependency, so package is either a dependency or not, but rarely for purposes of cross-compilation, performance, and so on, compatibility, we want to separate out build time dependencies and runtime dependencies as two different things. So there's work that needs to go into designing, adding annotations to imports to suggest whether, in what scope particular imports make their values visible. There's work that needs to go into Cabal to make it differentiate between runtime and build time dependencies, and there's obviously work that needs to go into GHC to make it understand all of that, but that's something we hope to do in the very near future. So that's one thing that, yeah, is in progress. There's a question there.
So this was not a question, but something that I have been a user of, but didn't actually create, but it will be in 9.12, is that you can now create constraint solver plugins that are sound, because they can track their dependencies.
Yeah, the issue there is that a type checker plugin might say, I might be doing a proof that, I don't know, 2 plus 3 equals 5. Now that has no free variables, so that little proof is fine. But if the proof that it does in this constraint domain that it understands and GHC does not, if the proof that it is doing relies on some in-scope given constraint, like I might be trying to prove that A plus 3 equals 5, and that might be true if I have in scope a given constraint that A is 3, right? But that would not be true if I didn't have that constraint in scope. So if I was to take that little piece of code that needed that proof and move it outside of the GADT pattern match, suddenly it wouldn't be right, it wouldn't be sound. And you might get a runtime seg fault. And we did.
Yes.
Right, and we did. Right? So really, the proofs constructed by the plugin should record the lemmas that they used, right, that are the in-scope lemmas, effectively, as free variables of that proof. And then GHC will know, oh, this little proof depends on P, Q, and R, so I can't float it out of the scope of P, Q, and R without things going unsound.
Yeah, I just want to note that I am not the author of this. I'm just a user.
You were just the author of the thing that crashed when,
yes.
When we didn't have it. So that is, yeah. Anybody else? Yes, Matthias. Thank you, Pedro.
Yeah, so we had a talk this morning on on tracing, right? So, and you all know about this HPC Haskell program coverage that we had for a lot of years, but it hasn't received a lot of love. So I think we're working with I think David Binder is also here. So we're trying to give that some more love. But it's more tooling related, right? But so the idea is that we're going to add more runtime tracing, like low-cost runtime tracing to GHC. So if your program crashes with a head, it's probably going to integrate with this new error backtrace. But you want to be able to see like the provenance of values that were consumed that caused the error, right? Because sometimes you can just see the, it says like crash on an empty list, but you don't know where that empty list is coming from. So yeah, so we're working on, so we have a fork where it works, but we're kind of finalizing the design of, runtime traces in error messages for GHC. But yeah, but it's still in progress. So I think that's why Simon hasn't heard of it yet.
Yeah, I also just have a small thing. It's already done, I think, since the last release of HLS, so this is relevant for all GHC developers. So GHC has these nodes, and often in the code base, these nodes are referenced, so C node and then some name. And so since the last release, I think, of HLS, you can automatically jump. So with the normal jump to definition that you can use to jump to function definitions, you can also jump to definition of these nodes in the, even if it's in another file in the project. So, yeah.
That's cool. I personally regard this as being the one of the most important but lowest tech innovations in GHC's code base, probably around half of GHC's code, or maybe a third, I mean, a lot of GHC's code base is notes. There are thousands and thousands of lines, and I read them, I write them a lot. I read them every day, and if you ever submit a merge request, you know that you are going to get a response from me saying, can you please write a note to explain how this works? It's just sort of lambda x dot, can you please write a note? So just be warned. Sorry, you had a couple of hands up. Yes, speak.
Another thing probably worthwhile mentioning is there's a bunch of work going on to improve the integration of GHC into build systems like Bug2 and Bazel. That's work going on with Mercury, with Ian here, with Cheng is also involved, a bunch of others who are not here. Also, Zubin is involved in some parts of this. Around making it easier to get out of GHC structured information about dependency graphs, build dependencies, and so on, improving one-shot mode, and in that context also a compilation server, and yes, GHC-M, and also one-shot mode support for bytecode. I'll be talking about some of these things tomorrow in the Bug2 Haskell talk. Yeah.
Before you pass the microphone away, does that support backpack?
No.
My turn. A few things going on with cost analysis of lazy evaluation. So a couple things. First of all, my lab mate Nicholas, raise your hand. Where are you? Hi, Nicholas. He fixed HS to Coq, which is the program that translates an older version of GHC Haskell into Coq. Was that 8.10.7, Nicholas? 8.10.7 what? Yeah, that's the one it's at now. So, you know, you take what you can get. Thank you, Nicholas, because before he tried that, it was totally broken and we were all very sad. Nicholas Coulthard? T-H-A-R-P. No. C. I'll go type it.
I like giving credit to the people who've done the work, right? That's what we want.
Yeah, I was just the one brave enough to come up here and say it.
That's exactly. That's it. You got a special bonus for that. Yes.
Yes, thank you. So that's one thing that's going on in our lab. That's my advisor Yao Li is leading a lot of this stuff. The other big things are we're trying to get a formalized implementation of finger trees into our cost model. So you might have heard Liao's talk. Was that yesterday or 2 days ago? I don't even remember anymore. It was about demand semantics in Coq. And so that's the next data structure we're hoping to get mechanized cost analysis for. Finger trees. Yeah. Cohen is on that paper, is on our paper too. And what was the third thing that we're trying to do is make that process automated, so it's mechanized in that there's a process that you can follow to translate functions into a version that will let you compute the cost of lazy evaluation on a particular input, but it's not automated. So it turns out that the calculus to compute that output, that new function, is a little bit more complicated than it looks, and the only person I know who can consistently do it off the top of their head is Li Yao, and that's not a very good compiler. So we're hoping to get it to the point where you can just put a function into it and press a button and give it the input that it's looking for, and then it'll just work. So that's what we're working on. Get in touch with my advisor Yao Li if you want to hear more about that, or me. I'm Laura Israel. This is no, Portland State University. Yeah. Thank you.
I just want to mention a project. So we mentioned earlier that there was a WebAssembly backend that's coming along very nicely for GHC and what have you. I have a project from last year which involved actually compiling WebAssembly down into a bunch of polynomials for running as zero knowledge proof. Anybody who wants to is welcome to try and figure out how to get that to be up to the task of actually trying to run this WebAssembly backend that we have for Haskell. but it is sitting there on my GitHub account as Starkify. It was funded by a company that no longer exists.
WebAssembly to polynomials?
Yes.
That sounds crazy. Like, you take an arbitrary WebAssembly program, you spit out a
I take an arbitrary
polynomial.
WebAssembly program, compile it, run it. When it's done running, I then trace the execution that it did, prove that that was correct, and then log that proof in a way that you can, so it runs in nlog n time, but then can be verified that it was correct in log squared n time on a blockchain. So you can verify that the run was correct in sublinear time.
Okay, good. He said non-committally. Anybody else? Should we move on? I've got just a few more things to wrap up. We have time? Yeah, okay. Great. Let's see. I just want to tell you a little bit about the GHC proposal process, which is the process that that leads to these number of proposals that we then end up implementing and putting into GHC. Just to tell you what's happened this year. So at this moment in time, we have had in the total history of the GHC proposal process 430 proposals. 88 says under discussion. That just means they have not been withdrawn, shelved, or accepted. But under most of these are not in a very active state. The right-hand column, though, is the changes this year. Right? So we had 36 new proposals, of which 22 are still in that sort of the limbo state. Why does it say -9? Maybe that's because there are 9 fewer under review now than were. So that's good. We've sort of accepted or rejected those. We accepted 22, rejected none. Did we reject none this year? It's very kind. And quite a few have actually been implemented. Yes, I'm sure you will. Yes. Okay, so just to give you the sense, there's a sort of ongoing process there that's actually happening, functioning reasonably well, I think. I'm not saying that all the decisions taken are perfect there, because it's, we're just a group of people trying to do our best. And it's a big, complicated language, but it is at least an open process which all of you can participate in, and I wish you would. And in fact, let me, if I just skip ahead to, here are the people who are currently on the committee. We have a kind of annual process. A couple retire, 2 or 3 people retire from the committee. Then we seek nominations, and really it's very open. You do not have to be a heavy-duty academic to join this. In fact, we specifically want people who are practitioners and who also are sort of hungry, have energy, and go and read papers and think about things, because if everyone is just frantically busy doing other stuff, they don't get enough done. So there's a shortage of intellectual bandwidth on the committee rather than intellectual, there's plenty of intellectual horsepower, just bandwidth. So I'm really grateful to these people, really grateful. I think we all should be, because essentially they're doing us a public service. But a lot of other people contribute to the debate, right? Because the debate on the the GitHub place is entirely open. But so what is that? What proposals did we accept this year specifically? Finer grain warnings about unused, at the moment, if you have a variable that's unused, at the moment it'll report everything that it's, usually read the proposal. It's a useful filling out the thing. Specialized with expressions we talked about. No field selectors. This just says you can not generate field selectors for data type declaration with field names, and you can do that on a per data type basis. Multi-line string literals we talked about. This part, extension lifetime framework, we'll come back when we talk about stability and articulating stability goals. I'll talk about that in a second. Haskell we talked about a little bit already. This is the making it levity polymorphic. There's a bit to do with HPC, the Haskell program coverage tool, and its TIX files. Linear Haskell is still evolving. And again, mainly filling out the envelope. This was a filling out the envelope kind of proposal from Arno. You can now, at the moment, GHC says there are 2 ways. The ways in which you can get a non-zero return code from GHC today are pretty limited. This proposal gives a slightly more flexible way to set the return code for your program. This is a fairly specialized question. import shadowing. Oh, this is an important one for stability. At the moment, if you import a module and the author of that module, who may be somebody completely unknown to you, adds a function to it that you thereby have imported, and you have a top-level definition of your own with that name, GHC rejects your program, right? Ambiguous use, right? It's going to, well, you have to say import shadowing. You have to say some extension, but it'll be in some language edition, and you'll get it automatically. So in love, good. Right. This went through very quickly because everybody liked it. All patterns, we talked about. Oh, sometimes we have proposals that are simply amendments to existing proposals when, in retrospect, we think, oh, that design wasn't quite right, or it needs further clarification. So if you see an accepted GHC proposal you think is not quite right, not clear, could be better, submit a pull request for an amendment. It'll go through very quickly. It's very helpful. And these proposals live a long time. You know, they'll be looked at for years. So the better they are, the better. Oh, wait. Mumble, I'm going to skip these ones, I think. These are all fairly specialized. Wildcard bind. Oh, wildcard binders in type declaration just lets you say you can use underscores in type declarations. Like if you say, if you got a, I'm going to skip it. Multi-line strings we talked about. These are the people. Yes. So that's what I really wanted to say about the steering committee process, except to say that we did spend some time this year thinking about stability. And particularly, we adopted some, we're saying we never really articulated explicitly what criteria we should use when evaluating a proposal. A proposal that, for example, breaks all existing programs, we might think it make the language better, but is that a problem? Of course it's a problem, but we hadn't really said so explicitly. So now we've written down, and you can see on the home page for the GHC Steering Committee, you can see the principles, and the principles include these general rules that are spelt out in some greater depth. Right, that says, and what does this mean? If it works with a version of GHC, it ought to work with the next version of GHC. That's a goal. We'll come back to it in a second. Provided you're using stable extensions. What does that mean? Well, it means that some GHC extensions, like, say, linear types, are by their nature experimental. And we don't want to immediately tie ourselves down to saying, we will never break anything, or at least we will, bend over backwards to stop breaking and have deprecation cycles. No, some features will label as experimental, and that means, the next version we might break it, right? Because it will change, perhaps for good reason. But stable extensions, you should know. So the idea is just so that if you're going to stray into experimental territory, we want you to know so we're going to classify all extensions by their stability. And indeed, and this proposal here defines, in fact, 4 categories. Experimental, that's what I said. Stable, that's what I said. Legacy means we don't really like it, but we're going to keep supporting it forever. And deprecated means we don't really like it, and we might well stop supporting it, but we probably won't tell you when. Right? So the difference between legacy and deprecated is a bit, is not very much, but in the end we decided to have it. Okay? So this is just to say that as a language design question, we're paying more attention to stability. And then the other thing I wanted to sort of segue into, for GHC more generally, not just the design of the language, well, also, I think there's been quite a big culture change, right, to pay much more attention to stability. So we get lots of stuff saying it's so painful to upgrade from one version to GHC to another. Who was I speaking to today that says they're still on 8.10? I was definitely speaking to somebody there. But yes, Cardano is still on 8.10. We're nearly at 9.12, right? But it's a pain to upgrade. I think this time it will still be painful, but I think it will be getting less painful because we're paying a lot more attention, So let me just point you to this page. I put a link here. We'll publish these slides. This is a little, it's only a Google Doc at the moment. I wrote it. It tries to say, what are the facets of instability? But so actually it turns out there's more than one. Some of it is the language design, maybe the language design chases. A lot else is to do with the changes in libraries, right? And also there's some issues to do with template Haskells. There are several sort of different angles. So I've written it here as a sort of multifaceted problem, right? It's not a single pain point. But the big goal is really, and how hard can it be, really? You get a compiler, it compiles, your program compiles, you get a new version of the compiler. Surely it should be able to do everything the old version did. What's the big deal? Of course it should be able to compile your old program unchanged. At the moment, it doesn't for things like, oh, but it comes with a new version of base. Oh, but there's no real reason, why you should be able to use the old base API with the new compiler. Why not, right? But it turns out there are reasons why not. It's not straightforward, but that's what this document is about. And I'd be quite interested, if any of you want to take a look at it, in which are the pain points that impact you. That is, which should be the priorities. I've said here, difficult to know how to prioritize. Which would be the primary priorities? Up to now, we've put a lot of focus on not changing the language too much, all these extensions, but I suspect that's not the main problem these days. Okay? So anybody got anything they want to, I think that's all I wanted to say about stability. Has anybody got anything they want to say about this? Because this is a complicated question, I think, with lots of aspects.
So how does stability of the language and stability of the GHC API interact?
Stability of the GHC API is another axis of stability. So for maybe everybody knows this, but you can use GHC as a library. For example, HLS uses GHC as a library. Quite a lot of programs use GHC as a library. But when you use GHC as a library, right, to say look at a Haskell program through the lens of GHC, what is the API that you are using? And at the moment, we don't have one. We do not have a written down API for GHC. So what happens is our poor, hapless users necessarily are forced to just say, oh, I like that function, I'll use it. And then I change that function, 2 weeks later, because I didn't know you were relying on it. So I didn't know you were relying on it. You didn't know that I was going to change it. This is bad. So we should fix the GHC API and say what it is. And that is a sort of, at the moment, an unforced thunk. There is a sort of project which Alexis announced nearly a year ago to say, let's do that. But I think it's lacked bandwidth. So anybody who's interested in helping design a GHC API would be such a help. Such a help.
So I mean, it's sort of users of GHC as a library, but also plugins, right? Because
plugins use GHC as an API, yeah. I would be thrilled, as a GHC author, I would be thrilled to know what API you care about. And once you start to write down the API, you think, does that make sense? It seems terribly ad hoc and messy. Let's clean it up. But until you write it down, you would never get there. So guys, this is the cream of Haskell. It's sitting right here in this room. Anybody got any other thoughts about stability? I'm surprised. I thought this would you'd all be sort of like.
I'm from Mercury, and which is a fairly large code base. But I had an effort to use the GHC head against our code base, which is over a million lines of code, and then. Actually, the experience is really good. I know there definitely the stability is issue, but as we actually incrementally support the GHC head, then we actually found that the benefit is much more bigger than the cost. So this is really promising, and I just found the newer version of GHC getting better and better. So I will talk about that.
Cardano, 8.10. Mercury, 9.12. Head, in fact.
So Cardano actually does compile with 9.10, but the problem is predictability of optimization. We have something where type families are optimized slightly differently in 9.2, 9.6 and higher, and our performance team says, no, that's not acceptable. And actually there's a big difference in allocations that we get. And I think it's the all or nothing thing that you mentioned. We can't really upgrade the GHC engine, the simplifier, and the libraries. Something changes it, and then we have to dig through hundreds of megabytes of core to see where it changed, and then try to massage things in the right way or find the right GHC options. And that or
fix GHC.
Yeah, sure, but that's often not quite trivial. Like I remember the discussions of the GHC call where we know that it's very fiddly to change options in the simplifier. If something is changed a little bit, then some packages will explode, and others, if we change them the other way, then lots of packages will get a lot slower. So, yeah. So maybe, yeah, that's how what I want to say.
Okay. Yeah, I was going to say in the fix, Simon, by the way, the fix is to refactor the core of the Cardano system. So you're going to have to basically completely rewrite part of the core Cardano. Now, it's a good thing anyway, because we didn't really want those type families, but we're going to have to rip them all out. And one of the things that we then have to do is make sure that all the uses, all the dependencies are also updated. We're going to have to make sure that the system still has the same functionality, and then double check the performance. So it's not something we wanted to do before we got our release out last week. Sorry, Sunday, this week.
It's funny, it's a kind of a role reversal. I'm saying you shouldn't have to change your application, we should just fix the compiler. And you're saying we're going to rip our application in pieces. Sorry, Christian. But there's something funny going on here. We should talk about it. Yeah.
So I was wondering, is performance as something that's marked as stability?
Yes.
It should be, yeah.
Yes. So it is difficult, because anytime somebody reports a performance regression, our heart sinks. Well, my heart sinks, because I think these things can be quite hard and expensive to find out even what has gone wrong, let alone fix. And yet, my goal is definitely for monotonic improvement in performance, but it's terribly hard to achieve.
Because I would say, let's say, since GHC 6.12, the only regression in terms of functionality on GHC has been deep subsumption. For the rest, GHC functionality-wise has always been stable.
Mm-hmm.
Maybe it's base that changes all the time, or there's lots of libraries that secretly use GHC API under the hood, which makes upgrading difficult. But otherwise, GHC has been pretty stable, right?
Mm-hmm. But performance is unpredictable performance is the problem.
But that's the main focus of this then.
And I think the way you could help us, I think, when all of you, if you come across unpredictable performance or performance regressions, it's really helpful if you can invest a bit of effort to distill down. I know it's hard to do, but it's almost impossible for somebody who isn't close to the application to do, especially if we don't have the source code, which we won't. Yeah, yes, I know. Yeah.
I meant more the stability. Is the focus on performance, or what's the focus of this whole stability? Thing?
Like I say, I think what we want to make, I don't know, the language stable, provided you use the same language flags. The GHC API would like to be stable. You would like to be able to use old versions of base, so you're not forced to use a new version, which might force changes, which has a big carry-on effect. And we'd like performance to be stable. I wouldn't say that we have a singular focus on making performance stability at the moment. Mm-hmm. That's partly because it's so hard to get.
But GHC proper, as in the compiler, has been stable in terms of functionality for a very long time now. So the focus must then be somewhere else, right? Either base or performance, or... But what has been the unstable part of GHC?
It's actually hard to know. When I said it's hard to prioritize here, it was because you ask different people, and their pain points seem to be different.
Okay.
Right. Often it's to do with libraries, though, and the library upgrade path.
Right. So base and everything that's
often, it starts with base, and that means that forces you to upgrade base, and now you can't use some library that you depend on that somebody else hasn't yet upgraded. Maybe all they need to do is upgrade the version bound, but they're on holiday. This ripples a lot. So being able to not being forced to upgrade could be a big help. Okay. I think we should wrap up. I just wanted to just show you a couple of graphs, which I do every year. This is the all tickets is the blue line, and open tickets is the sort of tan-colored line. So at least the slope of open tickets is less, but it's still regrettably positive. But it's not. It's sort of, they're kind of like straight lines. It's interesting. It's not. Neither of these seems to be accelerating. But we're up to well over 20,000 GHC tickets. It's a big, long-lived project now. Really is. And so we appreciate that. And just reporting bugs with well-characterized reproduction cases is fantastically helpful. So, the all tickets part, this is important, right? And you are contributing to that, even if you're not contributing to fixing them. It's really helpful to have good repro cases. Here are some figures that Ben produced for the number of contributors. Now, I think the figures this year look down, but we're only partway through the year, so we haven't finished. But I think the picture here, I think it's fairly self-explanatory. This is the number of people who've made one commit, the number of people who've made 10 or more, and so forth. So what does this say? It says there's a significant but not enormous base of people who contribute directly to GHC's code base. I'm so grateful to all of these people. It's just fantastic to work with such a good group of people. But I would love more of you to contribute, and that's a and to do that, you just become part of the GHC team. We published this. I think I told you about this last year. This is the GHC HQ sort of homepage, and among other things, it points to this subpage for the GHC team, right? And here is the GHC team. And to join the GHC team, you just send a pull request, right? That adds yourself to this table with a little bit of information, what sort of things you're interested in, and then you're very welcome to join the weekly calls. So the weekly calls are completely open. If you're willing to sign up here, and there is a consequence, signing up here means you're volunteering to do things, but then come along to the weekly call, and you will hear maybe a dozen people are typically there. It's not overpopulated at the moment, and then you'll hear the hum of the business. I mean, Loiter's a regular, and Zubin, of course, is there every week. I'm there every week, and you just then you'll hear in more detail than you probably want to know what is going on in GHC land. But I just want to stress, you are very welcome. Right? This is a community project. It's not some kind of little elite group. This is all of us working together to make this little part, the little GHC part of the big, rich, exciting Haskell ecosystem. Okay, any other thoughts, questions, observations? It doesn't just have to be about GHC. It could be about Kabbalah Stack or HLS or anything else. This is a sort of, but about the implementation and progress of the ecosystem generally. All right then. Thank you very much for all your contributions. It's a lot of fun. Actually, I spend a significant, like more than half my time. I think I probably spend hacking on GHC, and I still love it after 30 years.
Among other places, and we resume at 4 o'clock for the final session of the day. All right. Welcome to the final session for today of the Haskell Symposium. We're going to have lightning talks at the end of this session. We've got 3 registered so far, but there's still time to register more. We're going to do lightning talks in the order in which they're registered for the lightning talk speakers. But before we get to that, we have a couple of presentations. The first is by Momoko Saito on controlling computation granularity in float.
Thank you. The title of this talk is Controlling Computation Granularity Through Fusion in Improving Floating Point Numbers. I'm Momoko Saito from the University of Electronic Communications in Japan. And this is a joint work with Iwasaki, Kawabata, and Komiya. Let's start with the background topic with floating point numbers, numerical errors. When calculating on a computer, if often used floating point numbers with finite precision. For example, computing 1/7 results in 0.142, but we must round the result to a fixed precision to represent this in a floating point number. But this causes rounding errors. Each rounding error might be small and insignificant, but small errors can become critical when they accumulate. So one famous example is Rump's example. And this is known for its catastrophic cancellation of significant digits. The exact result is here, but if we perform this computation using double precision, the result will be completely inaccurate due to rounding errors. So we are developing a Haskell library for exact real arithmetics, which we call Improving Floating Point Numbers, or IFN for short. And IFN provides a numerical data whose accuracy is gradually improved by demand-driven recomputation. So it has an infinite number of significant digits. For example, computing 1/7 IFN automatically enhances the accuracy of sub-expressions by needed, repeating the computation until the result meets the required accuracy. So by using this IFN library, now we can accurately compute Rump's example. Simply use the IFN type and specify the accuracy using accurate value function. There's no additional complexity. If the accuracy of the result is set to 40 bits, a result with an accuracy of 79 bits is obtained, thanks to the computation mechanism. So how the recomputation mechanism is implemented? In this slide, we explain the internal mechanism for IFN. And the IFN library consists of the IFN layer and the Q layer. The IFN layer is responsible for performing recomputations, and the Q layer only performs verified numerical computation required by the IFN layer. So the Q layer has no recomputation mechanism. And the IFN layer has object of the IFN type, which we call IFN data. And this rounded item represents IFN data, and each IFN data corresponds to each sub-expression in the program. And they are connected by the arrows representing a propagation flow of the computation requests. So the explained demand-driven recomputation mechanism is achieved by using the entire graph of the IFN data. The Q layer has object of the Q type called the Q value. And this squared item represents Q value, and each Q value is an internal data representing an accuracy verified approximation held by a corresponding IFN data. So now we explain the recomputation mechanism. Suppose that the recomputation is requested for this IFN, and the demand propagates along the arrow to the appropriate IFN data, especially to nodes lacking accuracy. And when the propagation reaches the end of the graph, this IFN performs approximate computation by calling interval arithmetic defined on the Q value. And it obtains the resulting value with improved accuracy, and by using this new value, the core IFN also performs computations like this. And here, these Q values where the recomputation did not propagate are reused during the recomputation process. This reusing mechanism minimizes the execution of recomputations. As explained in the previous slide, the current implementation of IFN treats every sub-expression as IFN data. On the one hand, this minimizes necessary computations, but on the other hand, it increases the cost of recomputation control. Specifically, it increases the memory overhead by enlarging the computational graph to maintain, and it also increases the time overhead by frequent interactions between the IFN layer and the Q layer. But unfortunately, the disadvantages of the latter are significant. So the program using the IFN library are slow and require much memory. So there are limitations on the scale of possible computations. One of the main reasons is that the computation granularity of IFN is too fine. And here, computation granularity is the unit of recomputation handled by IFN data. So in this research, we aim to improve the performance of the IFN library through controlling computation granularity by fusion. Fusion is a program transformation combining multiple IFN nodes into a single node. So the more IFN nodes fused, the larger the computation granularity becomes. And here, we propose two effective strategies, maximal fusion and chain fusion. Additionally, we successfully implemented a fusion system within DHC that automatically performs compile-time program transformation based on these strategies. As a result, users do not need to modify their programs to utilize the fusion. And now, we explain the main idea of fusion. This slide showed how fusion works with controlling computation granularity. First, we have to determine the IFN nodes to be fused. This slide shows just an example, but we can choose any connected nodes at the fusion target. And then, the fusion shifts down the computation of fusion target from the IFN layer to the Q layer. The computation of a fused node in the IFN layer is not only performed in the Q layer. This is the essence of the fusion. But the fusion sacrifices the recomputation mechanism of fused node for efficiency. And finally, the computational graph is reduced by removing the intermediate IFN data and Q values of the targets. Thus, fusion decreases the number of IFN data by increasing the computation granularity. But if the computation granularity becomes larger, the unit of the computation also becomes larger. So fusion changes the recomputation control. In this slide, we explain about this. Suppose that the recomputation is requested for this IFN, and demand propagates along the arrow in the graph, and this IFN performs interval approximate computation using the Q layer. But with the larger computation granularity, additional computation in the Q layer might occur. This is because fused IFN nodes compute its value by using multiple Q values, and some of them might not be computed before fusion. In this slide, this Q value was not computed before fusion, but after fusion, this value becomes computed. And one Q value is sufficient for one IFN data, so it is not necessary to keep these Q values permanently. Thus, these are temporal Q values. And the computation proceeds as explained before, and this Q value, which was not computed before fusion, is also computed. Finally, the requested computation is complete. And here, we summarize the merits of the fusion. The purpose of the fusion is to reduce the computational graph and simplify the computation flow. We can see that the number of IFN data and Q values and the interactions between the IFN layer and the Q layer decreased from 5 to 2. But there are also demerits of fusion. With a larger computation granularity, the number of Q value computations required for computation has increased from 3 to 5. Additionally, evaluating the IFN node requires as many Q values as the computation granularity. So before fusion, each IFN node needed only a single Q value, but after fusion, each node needed 2 or 3 Q values to evaluate the IFN node. Thus, although the computational graph has become smaller, the required memory to evaluate the fused IFN node may not decrease as expected. And next, we explain the 2 fusion strategies for effective fusion. The first strategy is maximal fusion, or MF. Here, MF fuses the multiple nodes for IFN expressions that are maximal. And the IFN expressions means IFN type expressions composed of only basic arithmetic operations in the function. And here, we show an example of the maximal fusion. In this example, x plus b plus 1 and sine of 3 times x and cosine x are all maximal IFN expressions. If we apply the maximal fusion to this program, we obtain the lower program. But it is not necessary to understand the transform program, and we want to give a flavor of the transformation. The maximal fusion transforms these maximal IFN expressions into these expressions with internal functions, and they're performed in the Q layer by fusion. And the second fusion strategy is chain fusion, or CF. CF fuses multiple nodes across recursive function calls, forming a chain. And here, chain is the shape of a computational graph structure created by calls to a linear recursive function when combined with the maximal fusion. And here, we shown an example of the chain fusion. In this program, bar divides 1 by 2n times and returns the result using bar subfunction. And the bar subfunction calls itself recursively in the IFN layer. So in this example, bar subfunction is the target of the chain fusion. If we apply the chain fusion to this program, we obtain the lower program. Again, it is not necessary to understand this program. And the chain fusion transforms bar subfunction into bar prime subfunction, and it is called by bar function. And here, bar prime sub is also a recursive function, but its recursive computation is performed only in the Q layer by the chain fusion. The chain fusion changes the type of computation of the recursive computation from IFN type to Q type. So that before chain fusion, the recursive computation is defined in the IFN layer. So its computational graph is built in the IFN layer. But after fusion, the recursive computation shifts from the IFN layer to the Q layer. So the computational graph with only one node is built in the IFN layer, and instead, the recursive computation is only performed in the queue layer. This transformation process is similar to the worker path transformation, and it is a technique for changing type of a recursive computation. But here, we omit the detailed explanation. To estimate the effect of proposed two fusion strategies, we defined two metrics: the maximal computation granularity and the estimated space cost. The maximal computation granularity, G, is the largest of computation granularities. And the estimated space cost, E, is the space required to execute the program. And let the maximal computation granularity be G, and the number of graph nodes be N. E is the sum of the cost of maintaining computational graph, and temporary working space for computing the first IFN node. Let's consider with this example. Before fusion, G is always 1, and E becomes this value, where N equals 5. After fusion, G becomes 3, because it is the largest computation granularity among 2 in left node and 3 in right node. So E becomes this value, where N equals 2 and G equals 3. In the previous slide, we talked about the chain fusion, but there is a problem. When we apply the chain fusion, we have to care about the chain length to be fused. It is because fusing two long chains brings large computation granularity, and as a result, leads to performance degradation. So, to address this problem, we split the fused chain and adjust the computation granularity appropriately. This slide shows a case that the long chain of IFN node is fused into a single IFN node. In this case, the decomputation of this IFN requires a whole recursive computation in the queue layer. And of course, it also requires a large amount of space for temporal queue values. Here, if we split the long chain into two, the unit of recomputation becomes smaller, and the space required for the temporal queue values are also decreases. This is how splitting a long chain solves the problem with the performance degradation problem. But how to determine the adequate chain length? And here, we determine the chain length using the matrix discussed before. And based on the estimated space cost, we can easily to show that the optimal split number is square root of Mn. And here, M is the computation granularity of one recursive computation, and N is the chain length. And here, we summarize the proposed fusion strategies. We proposed two strategies, maximal fusion and the chain fusion. The maximal fusion applies to IFN type expressions that are maximal in the function. And chain fusion applies to linear tail recursive functions. And these strategies improved estimated space cost, the complexity by constant factor and the square root of chain length factor, respectively. The maximal fusion can be applied to many programs. It is highly general, but the effect is relatively restricted. And the chain fusion can be applied to only linear tail recursive functions. Although it is less general, but the effect is relatively significant when combined with the maximal fusion. And now, we explain the implementation of the IFN system. The IFN library consists of the library part and the fusion system part. The user program only uses the library part at runtime, and GHC uses the fusion system part at compile time. And here, we focus on this part because discussed fusion is implemented in this part. And the fusion system part is divided into the source plugin part and the metaprogram part. The source plugin part is inserted in GHC's compilation process. And the metaprogram part is used by template Haskell to perform the fusion transformation. And this slide shows how fusion system works. And the fusion system invokes the GHC compiler twice in this, as shown in this diagram. The first compilation process traverses the ASD after type check-in and detects the fusion targets. And we used source plugin capability to insert this process into the compilation process. And detecting the maximum fusion target is relatively straightforward by using type information of expressions. And to detect a chain fusion target, we assume that the user provides specific annotations to each target for simplified implementation. And then the positional information of the detected target is written to an external file. And the second compilation pass performs actual fusion transformation. Using the external file, another source plugin inserts the template Haskell quasi quotations into each fusion target. And then the template Haskell expands quasi quotations according to the definition of the metaprogram part and generate a program representation after fusion. And next, we go to the evaluation of the proposed fusion system. We conducted the experiment using numerical computations. And we compared 3 different fusion systems, no fusion NF, and maximum fusion only MF, and a combination of maximal and chain fusions MCF. As benchmarks, we implemented 5 subjects from the many-digit friendly competition at the Haskell program using the IFN library. And here, MCF was applicable to only 2 benchmarks, logistic and harmonic. And the evaluation setup is presented here. And here are the experimental results. Left side shows a required memory, and the right side shows execution time. The benchmarks are divided whether MCF is applicable. And the vertical axis represents the ratio to the no fusion case. So the lower value is the better. About required memory, MF required about half of NF. And also, MCF required at least memory only about 4% in the best case in harmonic benchmark. These results showed a similar tendency to the number of IFN data. So we can say that reducing the number of IFN nodes in the computational graph using the proposed fusion strategy was very effective to reduce the memory usage. For more detailed information, please read our paper. And about execution time, we can see both decreased case and increased case. For decreased cases, they were about 70% of NF. We believe this speed up thanks to the IFN data reduction. Specifically, the eliminated the interactions between the IFN layer and the Q layer, and the decreased GC overhead. But for increased cases, it was about twice of NF in the worst case in the Hilbert benchmark. We consider this slowdown due to the increasement of recomputations caused by additional computations in the Q layer or a higher frequency of recomputations. But overall, the experimental results showed the effectiveness of our proposed fusion system. In this talk, we proposed fusion and two fusion strategies for controlling computation granularity of the IFN library. We introduced maximum fusion and chain fusion strategies and implemented them in a fusion system. And its effectiveness was confirmed through evaluation, shows that reduced required memory at least 50%. And we also observed a speed up in some cases, thanks to reduced overhead. Yeah, that is all on my presentation, and thanks for listening.
Hi, my name's Christian. You showed the two-pass system for your compilation. First using a source plugin, then finding where you want to splice in things. Why couldn't you do that in one pass? If you go to your implementation strategy.
Okay.
So what in GHC is missing that you could do this in just one? What's missing in the Glasgow Haskell compiler that you couldn't do this in one pass?
Okay. We have to modify the program to fusion transformation, but we implemented fusion transformation using the temporary Haskell, but to determine the fusion target, we want a type information, but template Haskell is move before the type checking. So we divided compilation process into.
So you looked at ways that you could sort of divide up your chain fusion to, manage the space-time trade-off. Did you look at similar ways you could divide maximal fusion to sort of better trade off space and time in some of these examples where maximal fusion seemed to cause a serious slowdown?
Yeah, sorry, could you repeat the question?
So maximal fusion seemed to cause a slowdown in a pretty bad slowdown in some of your examples, right? Yeah, so could you have done slightly less maximal fusion to get at least better execution time at the cost of a little more memory usage?
Do you have a question about the maximum fusion, the more optimization of the maximum fusion? It may be difficult because the maximum fusion is based on some heuristics, and the expression in the one definition or one function is not so big. So the fusing such an expression is not lead to so many degradation, but the result showed some degradation. So yeah.
Yeah, so a question about this graph. So I noticed in some of these benchmarks, the black bar is missing, yes. The MCF one. Does that mean it's so small, it's basically zero? For example, what is the MCF strategy not applied at all for the Hilbert?
Yeah, MCF is also applicable, but the transformed code of MCF and MF is the same. So it is not need to present the result in graph. Thank you very much.
All right. All right, next, Ian Woo Kim will tell us about how to ignore everything Simon said about stability and just run the latest thing you find on GitHub.
Oh, sorry, sorry. Yeah. Okay. So first of all, our company is quite a young company. We are a startup, but we are actually providing a banking service for startup, and actually we are quite fast-growing startup. And currently in the business domain of this banking for startup, actually we are currently the industry leader. So as we grow, we already reached almost 200 engineers right now. And in fact, our software stack is actually quite monolithic and, in a sense, quite simple. It's basically doing the web application for full banking operation. As you see from any bank web page, we are basically providing those services as a software stack. And our backend is really completely written in Haskell. And our front end is in TypeScript and React. And also our infrastructure is basically managed by the Nix for the underlying dependency management. Yeah. So as you said, since backend is completely written in Haskell, so with around this 200 engineers, almost 2/3 of those engineers are all Haskellers. So we are fairly large Haskell shop right now. And so, as I said, we have a really big monolithic app, Haskell app. And the backend is basically just configured as just a single repo. But inside that repo, we have basically our build is a cabal, and then we have around 60 local cabal packages. And however, most of the code, those code in the local packages is quite small, but the code in the actually one giant main package, which is called the MWB, Mercury Web Backends, has almost over the 10,000 modules, and the size of the code is already reached the 1 million source lines of code. So it's a very fast-growing and then the very large code base. So as you see from the graph from the 2021, actually around the time we had around the 1,200 modules or something like that, and then right now within 3 years actually we reached that 10,000 modules. So it's a very fast-growing, and of course that means we have lots of the developer pains with that kind of growing scaling. And also very interesting point about our code base is it's very template Haskell heavy code base. So yeah, yesterday I actually counted, and actually 4,800 modules were using template Haskell. I counted it. And so that's among the Haskell code base, actually big Haskell code base, this is rather some unique features of our code base, I think. So this is mainly because we use ESO web stack, and then also we use the PostgreSQL, but we always have some template Haskell bindings to each PostgreSQL database schemas, and then we also use template Haskell in lots of the business logics. So that's our current code base. And however, I'd like to actually
proud of ourselves and also hold the Haskell community, GHC community. The build is really fast, actually. So it's on my laptop, this laptop. Actually, it takes only the 8 minutes and 30 builds for this million lines of code. So I think and compared with other languages, I think this is a pretty much a big achievement, I think. Also, if I count that as the dependency footprint as external Haskell packages, not inside our monorepo, it's about 550 external packages were our dependencies. So this is a kind of a scale of our current development. So, and I'm in the company, I'm in the role of this compiler engineer. So basically, I'm taking care of any issues related to GCC. And I'm inside the backend developer experience team, which is inside the big platform team, which is taking care of all this stability or infrastructure and developer experience, those kind of issues. So, oftentimes the people, developers, our engineers are complaining about some issues in, stability or some kind of some shell command failure or something like that. And basically, I'm judging whether it is a GHC internal issue or not. And then if it is GHC issue, then I'm trying to solve that issues, or I will also report those things to our collaborators, GHC collaborators. That's mainly what I'm doing. And so for this kind of collaboration, definitely we need to have an external support. So there are really lots of the GHC issues I encountered, and then I cannot solve, or even I cannot imagine how can approach those problems. So we basically currently working with a tweak and well-typed, and actually some of some of these collaboration are here already. Yeah. So this is basically the GHC, mainly GHC expert, and also two build system experts from the tweak, including Andreas here. Yeah. So, in fact, the collaboration group is I would say around 10 people, I guess. Now, the 9 to 10 people, but depending on the consultant group's situation, we have some kind of time share and rotations. But basically, we all share about some issues around our Mercury code base, and then basically we discuss and then distribute such works, and also consult with the upstream people as well. That's I call it GHC collaboration around the Mercury. Then this kind of our collaboration actually, I think we are contributing back to the GHC and Haskell community quite well. Basically, we are integrating the GHC as early as possible and finding issues from our integrations, and we are basically working as a kind of a quality assurance of GHC in a sense. And also sometimes we need some new features of the GHC, so we want to prototype and derive such a feature development and contributing back to the upstream. Okay. Yeah. So in fact, my story actually starts from some special feature which was originated from our collaborations, which is called, we internally call it template Haskell bytecode linking, which is basically in terms of GHC options. It's a prefer bytecode, write interface, simplified core bytecode and object code kind of things. Yeah, it was from that collaboration. At that time, the Alex King 2 week identified using our code base, the template Haskell compilation has some kind of bottleneck, and it can be greatly reduced. The template Haskell, if you just schematically see, so if the module A depends on some template Haskell module, then when A is compiled, then the template Haskell module is of course previously compiled. Then basically GHC invokes some kind of mini GHCI session, run interactive or something, and then that basically load the template Haskell precompiled objects, and then start the interpreting evaluation of the splices. But actually that load object, which internally calls the dynamic open system call, that has some kind of a weird OS level
locking behavior. So we actually don't understand what is happening really well, but underneath the phenomenologically, we see it actually hurts the build parallelism a lot. And but when when this collaboration implements this prefer bytecode, then we are basically the template Haskell code is compiled to the core, and then the core is simplified, and the simplified core is serialized into the Haskell interface file. And then when the A module is compiled, then this GHCI calls this init whole core bindings, and then basically deserialize this core, and then on the fly it compiled to the bytecode and load it. So although that has some overhead, but it's much smaller overhead than this load object, that we found that this really improved our build performance a lot. So we benchmarked it on the Linux with 32 cores. Then it got like from the 12 minute 40 seconds to the 4.5 minutes builds when it was the 5,000 modules. So this is really, really exciting news, in fact. So in a sense, this head integration strategy, I would like to just describe, is started for this benchmark. So that was prefer bytecode was shipped in GHC 9.6.1 release, and we were testing that feature since the 9.6 the release candidate, and basically, we just really want to test that feature and then want to benchmark it. So we want but our build was fully Nixified and hard to actually modify with the custom GHC. So we made kind of a temporary the build outside of our repo. And then with that temporary build, we started the benchmarking. And then, of course, at first it was a really hard task, and that kind of an onerous task, because we had at the time around 400 external packages, and GHC 9.6 didn't, and it wasn't released, so we had to adjust that for the build. And of course, the number one actually enabler for that the effort was at the time the head.package the effort was started, and for the foundational packages, those lots of the external packages depending on the foundational packages which need to be adjusted for the GHC head was actually can be quite well adjusted with the head.package. But of course we need to few tens of library libraries adjusted for that GHC 9.6 build. So, in fact, we are lucky because the 9.6 branch was not that diverged from the GHC head at the time. So, and then that's the result from that is the number I showed. So, result was so promising, and we were so excited about that. So, yeah, okay, 9.6.1 release came out last year, and then actually the GHC 9.6.1 saga happened, and for me, it was a kind of a nightmare at the time, because 9.6.1 release, after the 1 month of the Nix integration, we hastily delivered that GHC 9.6.1 to our developers, and then suddenly segfault happens everywhere. That segfault happened especially on the MacBooks. Not especially, just only on the MacBooks. So I was testing everything on Linux, but I didn't catch this one. So when we testing, it has a segfault, and when we build, it segfault. So it turned out that it was an RTS concurrency bug on ARM architecture. So if we look at actually history of the GHC commit, when we go to the 9.4 to 9.6, actually RTS memory model changed a lot at the time, especially the memory access operation is not, from then on following the C++ concurrency memory model. So that means basically we are not using the explicit memory barrier for the assembly, but we are using some load acquire, the store release, memory fancy operations. But unfortunately, that was not complete around the release. So the transition was incomplete, but it was not caught by the developer's eyes. So then the ARM CPU, which has the fairly different model on this memory model got caught by that bug. So Ben Gamari was working on that issue, but that work was quite 20 commits across the multiple branches, and then we need to cherry pick the relevant ones as soon as possible and test. So, as you know, this kind of a concurrency bug is one of the most hardest bugs you can actually fix. So it happened 1 in 20 full builds on my laptop, roughly speaking. And of course, the more codes, but the more frequent, but it was really, really hard. So, yeah, so at the time, because I already had this kind of benchmarking the setup, so I had to work on that for that fix. So, so in this case, really testing multiple branches on the GHC head was really necessary. So, and then whenever I just change it and then compare the different commits and whether that works or not, then as you know, I have to, if in normal build setup, I have to build all the dependencies, 380 packages, which usually takes 3 hours. And it was a really painful the experiment. So basically, I just used that, somehow the Cabal's inability to detect the GHC binary changes. So we built all the dependencies with a certain version of GHC, and then swap the GHC. But that it doesn't change any hashes, and then our target project is just built with the different versions of GHC, and then with that test, actually, finally we found that the right commit for solve that issue. Okay, so now that problem got happily solved by cherry picking, but in fact, on the upstream, it was solved, when the GHC 9.6.4 was out. So it's quite a significantly later. But for us, this is a very crucial the strategy. So I just found that this is really useful, and that this is really helpful for our thriving, basically. So from then on, basically, I made a strategy like we always follow the GHC head, and we always follow also our project head. So it's a double head chasing, but it's hard, of course. But once it's done, and then every work is incrementally done, so it's quite doable. So we start to support the GHC head and then 2 major releases on 2 the major platforms, and of course this head packages was a key enabler for that. Okay. Then our efforts immediately actually rewards myself, because we were able to test the GHC 9.1 just before the release, or I think just after release, I think, and then we just found that it has a very serious memory leak bug, and with our repo it reached the 100 gigabytes. So that issue was immediately reported to Jubin in our collaboration. Actually fixed that issue in just a few days later. But unfortunately, that was just after 9.81 out, so it's fixed in 9.82. So it would be real hassle if we really hustled to the GHC 9.8 upgrade. And then with that setup, we found another memory bugs, in fact. So the GHC, I had some memory retainer bugs with the mode interface, with also the lazy I/O, and that also gives a by the iteration we actually found that bugs, and then also fixed it to that. And also, it's not bug, but in fact the GHC mode interface has some very inefficient representation. So seldom used data structure is just occupying memory all the time. And then basically we just got rid of those unnecessary things out of that. So I'd like to say, yeah, and then this work actually spawned a lot of the next new feature works, and basically the profiling. The GHC now supports the profiling and dynamic combined flavor, which is quite a new things. Probably if you build a recent GHC, you see it has a prof_dyn of flavor as well. That's actually from our efforts in profiling the GHC, and also the ERAS profiling and then the GHC debug improvement. Those things are all tested over the repo. So I would like to say whether it's sustainable with this double-head chasing strategy. You know, in fact, this comes down to the issue of the last Simon's talk. So it's about question about the stability. So basically, I just from my experiment with 9.7, 9.11. Most of the pain is not the language change. Language change is quite rare, and type check is always quite good with a different version of GHC. But the dependency update is really the pain. And then basically we have tiered dependencies. So normal dependencies are usually okay, but of course base and core library changes. So import should change it. Then we have to just change, adjust it. But template Haskell libraries are a little bit painful because template Haskell ASD often changes. But definitely GHC API dependent libraries or the tooling, especially code formatter, LSP, and plugins, they are quite hard. So it's kind of I need a little bit effort, rearranging our the repo to disabling certain plugins or something like that. So this is basically the issue of the GHC API stabilization. But anyway, this effort can be all shared among the across our community. So we have this nice infrastructure head package, so we can actually share those efforts, and then we can thrive together with the GHC head. Okay, so since I almost ran out of time, so I just mentioned briefly, and then that will be talked in tomorrow, the Andreas talk. So we actually, from these all efforts, we found that our scale is already reached. The Cabal may not handle our scale very well. So we are now investing quite heavily on the distributed build system. So we are currently working on that. And so the main plan is basically, so GHC make is currently like this. So it has this downsweep dependency analysis phase and then upsweep the compilation phase. But what the distributed build system means basically this whole the GHC make is deconstructed, and then basically all this the compilation action can be either remotable and also the artifacts can be cacheable. So in our collaboration, we are making the significant progress there. So in GHC upstream already has lots of the MRs, not everything is merged yet, but lots of the progress from this. And then tomorrow Andreas will show actually the working environment. Yeah. So this is a list of our the contributions. And then also it succeeded in building our project actually. And then we also definitely for this GHC head integration strategy need to integration with the new build system, and then we are also working on this kind of official support of head integration into that system. Okay, I will stop here. Thank you.
When there was a new feature in GHC 9.6 and you had trouble with 9.6, did you consider backporting it to 9.4 and using the existing GHC, but with the new?
Yeah, definitely. I mean, if I go back to that time, then probably that just backporting that feature to the 9.4 would be the more reasonable choice. But in the end, I end up with just making everything working with the head, and then that
from then on, actually, what I earned is much more than actually what I lost. So I feel like, I'd like just stay on this strategy. In fact, yeah, I think that this is a very good, although very aggressive, but a very good strategy for the whole community, I think, yeah.
So for future, you would again switch to GHC head rather than asking, like if you work with tweak or whelp types, for a feature to be developed against stable GHC. And
yeah, I mean, I would like to just, be more progressive, in that direction. Yeah.
Okay. Yeah, sounds good.
Yeah.
Lightning talk will be about solving type literals.
Yeah, hi. I'm going to talk about solving inequalities instead of inequalities on type level natural numbers. So what do I mean by that? Let's say you have this code, the GADT on top, a vector with the length annotation, and we have the standard cons, and then concat. If you want this to type check, the GHC will ask, or without a plugin, you would be asked to show the equality that you see at the bottom. And using high school or primary school, depending on your country, you can solve that through axioms and come to a conclusion that they are syntactically equal. And so we've had a plugin that does this kind of things for quite some time, almost 10 years. Still maintained today, works on the to-be-released GC 9.12. It can show fairly complex equalities involving exponentiation. And the only way this works is because the thing you see on the right is the chosen normal form. Like there's many normal forms we could have picked when you involve exponentiation. But there's a straightforward algorithm that expands the left-hand side to the right-hand side. And rewriting works very well when you want to deal with equalities. But it did not turn out very well for inequalities. So inequalities were sort of bolted onto GHC typeless net normalized and never really worked well. So it never worked it could not show transitivity of inequality. It just didn't. It refuses to solve it. And also there were bugs. So if you turn on the current plugin, you can build a proof that false is equal to true. So that's very highly undesired. Somebody can probably turn this into an unsafe course. You might be wondering, like, why not use SMT, use Z3? So me and my colleagues, we work in a field with lots of exponentiation. So not polynomials, exponentiation. So the non-constants are in the exponent. And we found that Z3 chokes very quickly. We've tried other SMT solvers as well. They just don't like to deal with these non-linearities. So we had to do something else. So at QBioLogic, we had a quite bright intern, Alexander Pokolitov. He built, I think, 4 plugins over the course of 20 weeks, including this last one. It will be if you've been using GHC typeless net normalized, this will be its replacement. It has a new solver based, again, on rewriting, also, some interval arithmetic, and also Newton's method for root finding as a backup in the case interval arithmetic doesn't work. So the solver is there as a library. The subset is currently only on GitHub. It has a SMT lib kind of interface, and we also use it in the plugin. It passed the complete test suite of GHC typeless net normalize, and it can finally prove all these things. So it can show transitivity, It can deal with other inequalities as well. That's the lemma 2. And it can finally move from inequalities to equalities. So if it knows that x is basically between 0, then it must be 0, something that the previous plugin could never handle. Let's say before the end of the year, this plugin will be on Hackage, and it will also be made sound. The thing that Simon mentioned in the GHC update, we still need to apply the tracking of our used lemmas in a way. But yeah, that's what I wanted to say. And on to the next speaker, I guess, unless there's some questions. All right, thanks.
I don't have a for a Mac.
Oh, I have one.
We're trying to get my Mac set up here. While I do that, so this started out as an experiment on what it would take to actually be able to make GHC a really good, strict language. Now, this is not how I would like to do that, but it was sort of, we started picking up a bunch of capabilities in that direction. We have all these runtime representations and what have you, and I would like to see if I could get Prelude to run that way. Let me switch my screen over somehow. Screen mirroring. Display settings, come on, just duplicate. Arrange on top of each other. To mirror, hold option while dragging. We change this in current. Hold on. Apparently not good at this. All right. Are we good? All right. So I started experimenting with what it would look like if we could take, I apologize for the size of the font, let me try and blow that up. A standard class, let's start with something like eq, and make it runtime representation polymorphic. Now I can define equals and inequality just fine. But then I go to define the default definitions for those. And now here's where we're allowed to have runtime rep polymorphism starts to bite me in the butt. So we can only be runtime rep polymorphic in the result position of a function. So I can have a function that returns a runtime rep polymorphic result, because we can do that to because I just don't care to call it if I'm just going to blow the stack or something like that, right? That's the kind of situations where you might be able to do this sort of thing. I'm going to invoke it, and it's going to call me back with the right registers, and therefore it's not my problem. Okay, that's sort of the trick. But but if I have to pass it, I don't know what kind of registers that is. An int rep is going to be an integer register, and adder rep is going to be something, some SIMD crazy thing, floating point register, what do you do? So what can I do? Well, I can punt the problem. I can make another class that's responsible for dealing with this, and then use default signatures to say, use that instead. That class doesn't know anything about my instances for eq, but it does know what my runtime representation is. Now what I can do is I can lift all the things from Prelude directly in, and then I'll make this eq rep thing. I have to make instances somewhere, though. Where do I put them? So the problem is something like this. Let's say I build this library, and then 2 people depend on my library. If they had to instantiate this class independently, locally, just because runtime reps are a big, nasty, infinitely long set of things, because you have tuple reps and stuff in there. If I need to be able to supply instances for all of the different possible runtime representations, I'm doomed. If 2 users came along and supplied the same instance. So where could I put them? Well, like if you go to a library called parsers, and parsec already existed, well, where would I put the instances for parsec? I could put them in the parsers library, Or I could put them in an orphan instance package and then hope that people try to pull up the orphan instance package. But at least if I put it in an orphan instance package, people would know where to get it from a canonical location. But how do I put an infinite family of things into packages on a canonical naming basis on Hackage? That seems somewhat problematic. I can't take an infinite portion of the namespace. But what I can do is I can use backpack, which is kind of a weird choice, and this is the wrong choice, and this is going to point to why I want something better, but I'm going to use the only damn tool I have to do this. So what backpack is, if for those of you who are not familiar with it, is a form of like applicative functor, an ML term, applicative functor syntax for Haskell, where we can parameterize a Haskell package on another package. I have to rush really, really fast here, so I'm going to try and get to the point. And what I can do is I can build a runtime, I can build a signature for a module that is, there is some runtime rep. I don't know or care what it is. Tell me what it is, and I will build code peculiar to that runtime rep. This knows what the rep is. Now the problem is I have to instantiate this package. So it turns out if I instantiate the same backpack package with the same arguments, I get the same package in the package database. Therefore, two users doing the same instantiation would get the exact same hash, and it won't look like there's this nasty diamond worth of instances. The problem is what happens to my cabal file, or the first problem. So I can build this. I can build the ability to construct these definitions and put them into scope. Now when I go to build the mix instances, I start picking up a few lines of cabal. And it goes, and it goes, and it goes. And unfortunately, GHC starts to run into a problem with maximum Linux command line lengths. So this uses approximately 2 megabytes per command line for several thousand commands. It takes several hours to compile, but it did work. There was a couple of extra lessons I did learn along the way that I want to hit really quickly, and then I will happily yield the floor. Okay, the first one was, so let's go back to our classes. So I can do eq, that works fine. I do ord, it works fine. We just have these extra like defines in terms of these default definitions you have to import once. We can do num. As a matter of fact, it works perfectly fine with GHCI. You have to disable like the memorization of what the last result was, because that assumes that it was in kind star. Type, sorry. I saw the look of disapproval. So you have to disable like it tracking, but other than that, it works. And with that, I can turn on rebindable syntax and add 1+1 at type int hash. Okay? There is a problem, but we can fix it. The first problem is that rebindable syntax is all or nothing. If you turn on rebindable syntax, you have to rebind all the syntax. And one of those pieces of syntax is if, then, else. So I lose access to if, then, else, or do I? So here's a thing that I found to work around most of the limitations about levity polymorphism, which is that while I can't take an A in negative position, I can take a unit double arrow A in negative position, because that is a computation that will return an A. Now, I'm not saying a function that returns an A. I'm saying an arrow from unit as a constraint to A. And so this is an action that takes an empty, no dictionaries, and then turns around and calls you back with A. And so when I go to build if, then, else, I can write it once and for all, and it works. Now what's important is this also has the correct semantics for if, then, else. Because if you go to do if, then, else at a runtime representation that isn't lifted type, you don't want to evaluate the X or the Y until you know whether you're true or false. You only want to execute the one you use. Fortunately, that's exactly what has to happen here. It gets delayed until it gets invoked. And the unit is sort of happily applied for you. So I just wanted to say, please don't fix it so that I can't have a unit arrow as an actual thing in GHC. This does lead to some very interesting things. I can build completely unboxed natural numbers where we have the, just the tupling of the things to make up. This was before we had unlifted data types. So I had to use unlifted sums and unlifted products to make everything. But we can actually build some number types that actually get some pretty good performance, and I can actually push right up to the edge of what one could theoretically do. Is this a good idea? No. But we can do clever things with it, perhaps excessively so. Like, let's derive maybe in such a form that it works over all runtime reps as arguments. And we have to dip into using that same levitation trick in order to be able to switch runtime reps without having to have an instance for every pair of runtime reps in order to be able to do the mapping. So this trick, this levitation trick, was really the only thing that made this possible. And so I wanted to showcase it in case anybody ever runs into something similar, and wanted to make the case for this backpack piece. But in particular, this really calls for something that is missing in GHC, which is I am stuck doing the job that a C++ compiler has been able to do for me since the Stone Age, which is to basically instantiate a template and then deduplicate the instantiations, right? Theoretically, if what we were to do was to put the equivalent of a template keyword that I could use for runtime reps or really anything in type that had to be grounded out and would be generated by that code module, that would be deduped by the linker using the exact same linker flags that we use in C++, then the compiler could do my damn job for me. I could shed 3,000 lines worth of cabal file and several billion lines, or billion characters worth of command line. So please, God, I am begging for some way to get the compiler to do this job for me, because I never want to do this again. Thank you. Any questions or? If anybody had anything, I'm happy to answer.
Have you considered using staging? So you take a runtime rep and return code of A to bool.
Yes, unfortunately, that doesn't make good libraries, though, right? Like, the problem is like, I want to, at the end of the day, have something that like participates in the type class ecosystem like everything else.
Yeah.
And it just leaves me a second-class citizen. Oh, and I can use a GHC plugin to achieve some of the goals, but I can't do the list and maybe constructions that I do. I can only do the type class extension.
Okay. Two on what? Oh, okay, thank you. Great, I'm Michael Adams. I'm presenting work that was actually done by a student of mine for his undergraduate research. Unfortunately, he couldn't be here, but most of the research is his work in this regard. I'm just presenting it. Okay, so, and a lot of this also is going to be talking about, while it is focused on the performance of parsing in GHC, I will be highlighting some tools that already exist that we found were very useful in diagnosing some of these things. Okay, so why are we talking about parsing in GHC? Well, the fundamental problem is that the current way indentation is specified in Haskell is rather non-extensible. For example, if you look in the spec, the way it's defined is that the lexer recognizes these 4 and only these 4 tokens as particularly special. What's even worse is that in between the lexer and the parser, we have to add this L function, which has about a dozen different cases, a little bit difficult to reason about, and even worse, we've got this parse error t function that's in red that calls into the future, into the parser, and asks, if I were to omit this token, will this generate a parser? Oh, it will? Okay, then I'll omit this other token. So there's actually a cycle between the L function and the parser function. And in practice, GHC does not use this L function. Instead, it involves sharing state between the lexer and the parser. So I addressed this problem about a decade ago, dealing with a more compositional way to express indentation rules. And with this system, all you have to do is add annotations here in red that specify that, oh, for this particular region, we are starting a more indented region. The vertical bars represent that these have to be aligned. And there's a whole calculus that goes with this. If you do these annotations, you can then follow through the LR construction, and we even ported this into an experimental version of Happy that supported these annotations. And we were able to demonstrate that this works in practice. Okay, so well, what's the problem? The problem was performance. Now this is, number one, this was research quality code. So we weren't attempting to get like lightning fast performance. We were just attempting to demonstrate that it works. But nevertheless, it did mean that your parsing time approximately doubles. And that doesn't sound too good. That doesn't, especially if we want to eventually get this upstream. However, I should note that this is the parser time doubles, not the entire compilation pass time doubles. So the question for a long time was, well, what percent of time does the existing parser take? If it takes, if the existing parser takes 30% and I double your time, well, I've just added a 30% overhead. If it's 10%, I've added a 10% or 1%, 1% overhead. Which of these universes do we live in? Well, when my student got interested in looking at this problem, initially I thought we'd have to be like benchmarking GHC and adding all sorts of different things. But it turns out there's already a library that makes this very easy to use. And so part of this talk is sort of advertising that library. Even if you're not doing parsing, this might be a useful library for what you're doing. And you can't really read it here, but what this library does is it uses the existing dedump timings flag in GHC, and then it extracts and generates some nice graphs where each line here is one of the packages within a build, and each of the different colors represents one of the passes. So the blue there is the simplifier, the green, I believe, is the code generation, and on the end, one of those small slivers is parsing. Now, of course, looking at it this way is a little bit difficult to get good statistics, so we did a little bit more data processing, and we're able to collect data on the 20 most dependent upon packages within Hackage, and we were able to get these results. And you can see pretty quickly that for small modules, for modules that compile quickly, parsing does represent a significant amount of the time, but for larger ones, it's a much, much less amount of time. If we change the axes to both be logarithmic, it's a little bit easier to see that there's some sort of a power law going on here. In fact, because the best fit is a square root, I suspect what is happening is that something else in GHC, not the parser, because the parser should be linear, something else in GHC is going quadratic. So there's something going on in GHC's general performance. The median performance then becomes, that's the green line, of 1.73% of time is being spent on parsing. So if we were to implement this indentation-sensitive parsing, maybe you expect that much of a slowdown, except that this median is weighting all packages equally. So if I have 10 packages that each take 1 millisecond and I double their time, versus one package that takes 100 milliseconds and I increase its time by 1%, those 10 packages are going to outweigh the one major package. So we did some aggregation. Instead of at the module level, at the package level, that then brings the median down to 1.6. Of course, if you're doing an entire application, we shouldn't be really looking at the package level. We should combine them all together, in which case the median is only 0.73%, or 0.7% of time is being spent in parsing. Okay, main takeaways. Dedump timings and time GHC modules are cool. They saved us so much effort, and if you're doing anything where you're like, I'm going to add this feature, will it hurt me? Where's the cost going? I absolutely recommend taking a look at those. We did some extra processing to aggregate numbers, and you can probably port that to other things beyond parsing. The code for that is available. We also packaged up the Happy prototype, which has been around for a while, but has never been merged upstream. So if someone is interested in taking that work from research quality code to production quality code, and maybe eventually we can get this into mainstream Happy, I would be very interested to talk with you, because I think this might be something that will enable a more extensible language. Like if we wanted syntactic macros in Haskell someday, we need some sort of a system like this. All right, thank you. Oh, and by the way, I do have multiple PhD and postdocs available, so if you're interested in improving language ergonomics, for example, a language where making GHC more extensible, please come talk to me and we can maybe collaborate. Thank you.
Okay, thank you. Can you hear me? Good. So I'm going to show you a little demo that I like, a little bit of fun I've been having. Some of you, a few of you may have seen it before, but I hope that most of you will not have done. So every now and then, I like to play with alternate random generation libraries. So surprise, surprise there. So here is an example, and I've got a little demo of a library called rgen. As you can see, it's just choosing some numbers and returning them in a tuple. So I just to set the scene, I want to show you that in action. So if I reload, that's good. Now I can just pick a random value, and you know, as you would expect, I'm picking 6 random numbers each time. Okay, so that's very unsurprising. This is exactly like random generation and quick check. What's interesting about this library is that I can also add some constraints. So let me just constrain, let's constrain A to be equal to F, say. Okay, so if we do that, and I reload, then, well, you know, the first and the last values are always equal. So I just want to emphasize here that there's nothing funny going on here. Right, this code does what it looks as though it's doing. Those are ordinary integers. That's ordinary Haskell equality. We are actually, this is working by generating about 100 test cases and throwing them away, and then ending up with the one that has equal first and last elements. So only 1 in 100 generated test cases is actually valid and passes the guard. But as you saw, it doesn't matter. Computers are fast. So that's okay. Let's see how far we can take this. What if I require B to be equal to E? And while we're at it, let's require C to be equal to D. Okay, so if I reload this, now they're palindromes. Whoa. 1 in a million values passes those guards, but look, it's still pretty fast, isn't it? Computers are fast. All right, let's see whether we can go further. Let's require, maybe A and B to be equal. Let's require B and C to be equal.
You don't like inequalities?
It's more fun with equalities. Let's just reload that. Oh, okay. No. There we are. So now all 6 values have to be equal. There are 100 satisfying values in a million test cases. Computers are fast, but they're not that fast. Okay, let's let's take C. Okay, so what's going to happen here? This is harder. We selected the only one of a million test cases that passed the constraints. Are your jaws dropping? Mine did.
What if you put the C equals 42 first, John?
If I put C equals 42 first?
Would that constrain it? So that
Let's try it. Okay. It's still the same, yeah. So I could have put inequalities as well, but they're less of a tight constraint, so you know, it wouldn't have made the point the same way. So what's going on here? How can this possibly work? Well, let's look at the code of the generator. What's going on here? Oh, good. Here is the generator type. So generators are just trees. They can fail. That's the new possibility compared to quick generators. They can deliver a value, or they can make a random choice. And that rational there, that's just the probability of choosing the first branch. So there's nothing funny there. And we can make them into a monad, of course, which you have to do. And here's the code for that. So if the first argument is a failure, then we fail. If the first argument delivers a value, then we just pass it to the second argument. And if the first argument makes a random choice, then we make a random choice. Now, that is exactly the code you would expect to write for this representation of generators, except for the blank line after the first clause. And sure enough, I'm going to put something there. Okay, so before we start before we start exploring the randomness in the first argument, if the continuation h fails in any case, no matter what we pass to it, then we fail immediately. So you might have been a little suspicious of this is-fail function. What is that? It's the secret sauce. That's where the unsafe perform IO is. Okay, so all that is doing is inspecting x. If x is fail, we say true. If it's something else, we say false. And if it's an exception, you can see that I've passed in an exception to h, then, well, we don't know that it's fail anyway, so it returns false. And we do not prune the search space. So the effect of this is just that the order in which I write those guard clauses doesn't matter at all. So you asked me for that, Kevin, and you saw it didn't make any difference. And the reason is because this bind operation fails whether it detects a failure in the first argument or in the second argument. So as soon as there's any guard in the continuation that fails regardless of the choices of some of the values of the other variables, then we can fail early. And that pruning leads to this very fun behavior. By the way, this is exactly the same trick that lazy small check used to prune its search space. All I've done, though, is I've applied it to random generation instead. There we are. That's what I had for you. It's fun, isn't it?
Is that kind of like cut?
No, it's not, because cut may actually throw away answers. Here, we're not throwing away any answers. We're pruning parts of the search space that we know can never succeed. Yes, it does actually. That maybe that's important. I haven't tried the other thing.
Does this approach mean you'll be evaluating h twice? And how do you keep that from blowing up exponentially?
It does mean you'll be evaluating h twice. It seems to work anyway, I think, because you usually hit that exception early on when you call h the first time. And so in practice, it doesn't really seem to be exponential. It is very easy to break this code, though. I have broken it in so many ways. But in its present form, it works fine.
Just a shower thought, but could you use these kind of fancy new delimited continuations that we have to, if it fails, then like pick the value and resume rather than retrying from the start?
Pass.
Okay.
As I say, it's easy to break this. I wondered for a while whether I could detect using the argument by writing to an IO ref, and that doesn't work at all, because that detects the first use of an argument, and it means basically that you can prune too much because you don't detect later uses. So there are many ways to break this, And it's difficult to promise that any other approach would work without trying it. Thank you.
Yeah, that concludes the first day of the Haskell Symposium. We'll be back tomorrow at 9 o'clock. Cheers.